Good morning and welcome to day 3 of our Senior Project Symposium. I'd like to welcome NAV Canada back to our symposium today. I see Mr. Nathaniel Monson sitting at the back there. And I think Mike's back somewhere too, isn't it? Oh, there you are. Okay, good. So welcome back. Today we have Lachlan McLean joining us here this morning as our presenter. And he's going to present his solar air heaters, a turbulent and laminar analysis. Take it away.
Thank you, Mr. Brook. So my name is Lachlan McLean. I'm currently attending NBCC in the Electrical Engineering Technology program, and I am in the Alternate Energy Systems pathway. My advisor is Mr. Legier. Just a quick overview of what we're going to be going through today. We have the introduction, which was just covered. We're going to touch on what the goal of the analysis was. We're going to look at block diagram and concept drawing to get an idea of how things are done, essentially. We're going to touch on the principles of turbulent versus laminar flow, and we're going to get into the nitty-gritty with the connections and the channels of the DI1110. Finally, testing results and then concluding upon it. So to be clear, these modules, they're not meant to actually heat a space. I want to make that perfectly clear. I wouldn't trust these things to heat my morning coffee. But they are great for the purpose of analysis for turbulent and laminar flow regimes. So that is the main purpose of the project. And the end goal, the conclusion would be which flow regime is best for a heater. So just looking at the block diagram overview, we have a forced fan circuit that incorporates airflow and with it velocity. We have the 2 separate modules for the solar air heaters feeding into the temperature sensors, which are connected to the data acquisition unit, the DI1110, which is connected with a USB to my computer for data collection. That's pretty much the overview of the whole system. The concept drawing, this really just gives you an idea of where things are in the system, how it's laid out, things of that matter. Of importance is along the bottom of the ducts, the temperature sensors are mounted. That is a distinction to be made here. That's about it. To start with turbulence. Turbulence is an unpredictable and messy flow regime. It's often got eddies, vortices. And in preliminary research during the project, I had found that turbulence actually has, if incorporated correctly, has the chance to increase heat transfer in a system. Of note, also, it does increase airflow impedance as well. You can have a range of turbulence elements in your system. You can have ribbons, you can have turbulators going lengthwise. For my turbulent heater, I chose to do aluminum ribs. The aluminum ribs are 24 gauge. They are 29 3/4 by 9 7/8 of an inch. They're a 1/2 inch tall by 1/2 inch wide, and they're 5 inches apart on the sheet. This kind of gets to the nitty-gritty. So the LM35 was the analog temperature sensor selected for the project. It features a 10 millivolt per degree Celsius scale factor. So I did want to touch on this. This is in order to actually reduce, because there is no true ground in the circuit, in order to actually introduce a lower potential in the common node, it's important that there are actually diodes between it and the common node. Just a moment. This is how it would actually be connected to the system with the DI1110. The TB1 is a printed circuit board that I have produced. It just features the diodes. Actually, I'll go back a slide just to show. It just features the diodes and the resistor shown there in figure 18. And then, of course, they're labeled as well as the concept drawing to match up. So this was the negative produced here at NBCC of the actual PCB I printed. As you can see, it's been signed off by advisor. It's got 11 revisions. The actual board itself, once produced, a bit messy, but this is it, and it does function as needed. Okay, so I'd like to talk about the testing. So what's important here is that, so we have the calibration test, which is important to actually determine the accuracy of the sensors for the analysis. I don't think I need to touch on how important that is. That was done via boiling water and ice water, dunking them in each, and then having a reference temperature to compare it with, and then seeing what the deviation is between the expected and the actual result. We saw our deviation both from just an average of around 2 degrees Celsius for the sensors, so quite uncalibrated. I was unhappy with this result. The second test was testing the impact that my fans have on the actual solar air heaters. And actually, this turned out to be quite an important test. So what we observed, or what I observed in the test, was that the fans actually cause a decrease in temperature in the cavities. That was my hypothesis before it, but it was nice to get some confirmation. The turbulent heater actually reached its minimum heater. So what that means is that it actually released more energy because they're unloaded. It released more energy into the environment at a quicker rate. This would be the test results for test number 1. I only did 3 cycles for each. That is a source of error, in my opinion. I should have done more. Should have been more like 5 or 10. Of note here is that I don't believe I was patient enough with my testing results, because I didn't fully allow the sensor to actually chill, as you can see, because the boiling calibration were only about 1, maybe 1.5 degrees Celsius off. So that, because we're at a vapor point, that's a more of a steady kind of benchmark to go off. Whereas I was using, as noted here, I was using a mercury analog thermometer, which was not the choice. Yeah, so roughly it works out to about 2 degrees, give or take, with both ranges of calibration here. So test 2, it really does help to have a visual here. The cursor is centered on the turbulent output, channel 3 here. And what we're looking at right there is the actual minimum. So that's 23.19 degrees Celsius right there. Of note is actually that these 2 points, just from here to here, the minimum of the laminar is actually 140 seconds apart, which is quite a substantial time. So the switches were thrown in the experiment at 160 seconds. The 2 minimums occurred 140 seconds apart. The laminar saw a drop of about 6, whereas the turbulent saw a drop of about 7. The parts list for the project is as follows. I was over budget only due to I forgot to incorporate into my original estimate the DI1110. Kind of a huge part of the project, I just didn't know it was to be included. And also the associated cost with making a printed circuit board. The original estimate, as seen here, was $400, and we are over budget by about $120, and the DAC accounts for about $80 of that. So concluding on the actual test results, the sensors need very direly, they need recalibration. The turbulent effect that I observed was very limited due to the fact that I only ran the 1 test, and this was due to capacity failures. So I chose an A23, which was the wrong selection of part. It only provided roughly 55 milliamp hours. It's not the choice. It really only run 1 cycle of the test is what I'm trying to say. So the accuracy needs to improve, but from what we could see, the glimpse we could get, we saw a quicker heat transfer rate out of the turbulent module with that 1 scope. And of course, more testing is needed because it's not that accurate at the moment. I believe that's it. I'm gonna have to ditch the charger here, guys.
Ditch the wall too.
No, let's just do it like that. It's kind of, wait, hold on. I'm just going to show the actual data collection, the data collection process. Ugh. Wow.
Cables.
Yeah.
You want to move the whole project closer?
I think I'm just close enough. Just.
Okay.
Yeah, so the channels are reading out accurately. I'm getting about 22.35. I'm getting about 21.4, which is within a deviation. And then the process of which would be to actually get the azimuth. And you also want to know, obviously, your relative location in case you want to simulate results. And of course, the ambient temperature of the outside air. Those are the two major things, is the azimuth and the actual ambient temperature for the setup. That's really about it, unfortunately, for the DI-110 data collection. It's kind of just set it and forget it. Yeah.
You're inviting us to ask questions now?
Yes. Yeah.
Okay.
Yeah.
Okay. Any questions?
I'll get my slide back up.
Lachlan, what was your analysis for your project exactly? I feel like we didn't really get much detail into that.
It was to determine which flow regime was optimal for the heaters, based on, well, turbulent or laminar.
And what did you determine?
The conclusion I said for the one test, I was really only able to see, I was able to see that turbulent was better, but I don't know how much I trust that result as it's one test.
So how much better was it?
It was really, there were only about a degree difference between the two for the drop. Here, I'll bring up the waveform, one sec.
So a degree difference temperature-wise, but really when we're talking about energy, we want to be talking about joules, kilowatt hours,
Right.
things like that.
Yeah.
So what does that degree of difference relate to in joules, kilowatt hours? Relate to in joules, kilowatt hours, whatever you want to use, is really what I'm asking.
Be based on the air, like the medium.
No, I know, but did you calculate what that, a degree is, we know that a degree is a transfer of energy, demonstrates a transfer of energy, and I think really the question becomes, again, when we're talking about solar panels, it becomes how much energy gets transferred more from the one of your panels than the other one, right?
Right.
So did you sit down and do those calculations? Did you?
I did not. I relied on the differential for the purpose of analysis.
Okay, but, all right, yeah, I guess you would need to know the maths.
Talking about the, I guess, the efficiency of the two approaches, right? You mentioned that the more of a load on a more resistance to flow with the turbine
Yes.
setup, which, how might you measure that and factor that into your qualitative comparison?
For a quantitative result, you would need to do a static pressure test on the actual system, whereas we're dealing with a rather viscous medium like air. The impedance, what I'm trying to say is the impedance introduced in this system is not so much so that you would need to think about getting a new fan or sizing a component in the system differently.
But might there be a higher cost associated with powering the fan over a period of time?
That is an excellent point. Yeah.
Or maybe simply a simple current measurement
Right.
with your two, the fans in the two systems might have been factored into that.
Yeah.
Lachlan, you're showing, these are results from your testing on your project, right?
Yep.
Did you use the DAC to capture any analysis?
I had captured analysis. Okay, so the issue that I had realized with that, and I didn't want to bring up during the actual presentation itself, was in the preliminary research, I had mixed up whether or not, basically I had read that turbulent produces a better heater. The misassociation I made was that that meant a hotter heater. It doesn't mean a hotter heater, it means it can move more energy in the same amount of time. That's what they were getting to. So when I collected data, oftentimes because of the capacity issue, I would be running it in without the fans, just off, right? So really all I'm seeing is the thicker sheets of aluminum radiating more heat into the cavity. And it really only dawned upon me once I collected some of the data that that's not really what I'm looking for. Actually, it was once I ran that second test, I realized this is this is what I should have been doing, right? So.
Yeah.
That's one of the difficulties of analysis projects here. It's not until you begin obtaining results and comparing results that you recognize some of the issues that may not have been obvious at the outset.
And as I mentioned, you need a certain airflow on the ribs to actually create the turbulence necessary to increase heat transfer rate. So without the fans, it's just not the same. It's really not. And I was unaware of that, and I was having capacity issues with my battery. So it's a component sizing issue.
While we're waiting for the next question, would you just flip back the test one results to see if there's
Absolutely.
something there on the comment? Oh, yes, you mentioned analog mercury thermometer, wrong choice. That
Yeah,
just an
big
accuracy
time.
thing?
Digital would have been much better, quicker response, more accurate.
Really? More accurate? You sure?
Actually, precise, because it would be the digit placement past the decimal. Yeah.
And you're sure that, you're still sure, so you would rather precision over accuracy, or? For me, whenever anybody says, oh, it's digital, it'll be better,
The accuracy.
Yeah.
What is,
I can show you, I can tell you many, many examples of which temperature measurement is one that's not necessarily true.
Yeah. And I think that touches on another thing is I was kind of jumping the gun, as I mentioned in the presentation. I didn't let it chill long enough, the actual reference temperature, nor the sensors.
so you're saying that
Like see how the
You were
reference
using-
temperature here is dropping?
you were using an analog thermometer?
Yes.
Okay.
Yeah.
So why do you think that that thermometer is less accurate than a digital thermometer?
It's got quite broad divisions on it, like for the 0 to 10. So you're kind of judging by eye in
But
between.
does that affect accuracy
Yeah.
or precision? Does that affect accuracy or precision, right? Maybe you should define accuracy and precision for us.
Yeah, that'd be great.
I know mathematically it would be the precision would be the depth of significant figures, whereas for accuracy it would be the number of significant figures in the actual string. For math, that is.
Accuracy, no,
Exactly.
no.
Then, sorry, I wouldn't know.
So precision is resolution.
Okay.
Most people grasp that concept, so you're right, the number of digits. Accuracy is how close you are to the actual solution
Right.
overall, so it's gonna vary, right? You know, you're not always gonna hit the target at the same spot,
Right.
but if you are hitting close to one spot all the time, you're very accurate.
Right. That makes sense. Repeatability almost? Or
Repeatability, that's right, okay? So for example, a resistor, a 100 ohm resistor, when we say 100 ohms, what do we mean? What is that value?
Not 100 ohms.
Well,
It's just off of 100
But
ohms.
it's the
within range.
nominal value, right?
Yes.
It's the value that we're in and around, right, okay? Plus or minus 5%, is that resolution or accuracy?
Accuracy?
By all means, it's telling us that it's nominally 100 ohms, but you expect the number to vary from 100 ohms, 105,
Right.
or sorry, 95 to 105.
Right.
That's accuracy. Okay, so let's go back to the digital and analog thermometer, and let's talk about why you think that the digital thermometer might be more accurate than the analog one.
I would say that most of them feature an actual probe, which would go in, and it's actually a metal, so the actual, it would heat up or cool down quicker. So it's more of
Oh, but that's, at that point, that's not accuracy,
Right.
that's,
a mistake, right?
that's slew rate,
Yeah.
right? Okay, that's a whole other thing, right? Okay, so keep going.
So
Response time, yeah.
the actual metal probe would probably heat up quicker, which would allow me to just gather the data, get in, get out, because I was kind of in a rush, and that's the result I got, unfortunately. Whereas the analog, I needed to give it the actual time to release its energy to get down to 0 or near 0 in the ice water.
Yeah, but again, I don't see, again, let's talk about accuracy. I know you're saying I was rushed and whatever, that's fine. Let's just talk hypothetically about accuracy.
Actually, we can talk about that too, but let's talk about where you're going first.
Okay, yeah, all right. So again, a digital thermometer gives you a reading. A analog thermometer gives you a reading. Accuracy-wise, why would you believe that the digital thermometer is any more accurate than the digital one, given everything else being the same? Okay, so both of them are sitting there and they have a dwell time that's long enough for them to capture their data and you get accurate measurements, okay? What makes you believe that one is superior to one accuracy-wise?
Sorry, I think it would be based in the precision, as in I might get
But
to.
that's precision.
Right.
That's resolution.
Right.
That's a different topic,
Okay.
okay? Again, accuracy and precision are two distinctly
Yes.
different things. You can have a high precision instrument that is not accurate at all.
Right.
And you can have a highly accurate device that has no precision at all. They are two distinctly different things. That's why we always talk about precision and accuracy, because one does not entail the other. Okay? So, again, just think about it hypothetically. Don't think of your experiment.
Yeah.
Just think of why would you, again, because you're the one that said digital is more accurate than analog. So why do you think that would be the case? defend your stand. Fall on your sword on this hill.
I would say I misspoke, honestly.
Well, maybe in some ways, but maybe not too. But I think that we need you to, if you're gonna say something like that, just be able to justify it, that's all. So that's what we'd like you to do.
So the accuracy of the analog mercury thermometer, you asked me about that?
Well, we're asking you to justify your statements.
Do you know how a digital thermometer works?
Not exactly, no.
Then why would you say it's more accurate if you don't know how does it work?
It'd be based on the digits available on the screen, most likely.
That's resolution then.
Right.
It's not accurate.
Precision.
That's not accuracy.
Like, do you know?
Yeah. Precision, yeah, I mixed them up.
I
Yeah.
mean, if you don't know how a device works, why would you assume it's accurate?
That is true, and it probably would differ based on the digital thermometer.
But it could
Can you guess how
also on
it
the
works?
analog thermometer. No, sorry, but analog thermometers, can be saying you can get a very highly accurate analog thermometer, but you can also get a really cheap one.
Right.
Yeah.
Sorry.
Like if you put two analog thermometers next to each other, and one was measuring 150 degrees and the other one was measuring 100.00, which is in a position. But the actual temperature is 100, which one's more accurate, right?
Compared to a digital.
I think you have to look into that, because that's very, very critical to
Analysis.
measuring, right?
Yeah.
You know?
Now, I don't know if you want to go down this
Well, did
path some more, but
were you done your, I kinda.
I got crossfire.
No, I kinda jumped in there, so.
Yeah.
Honestly, I felt I was helping.
oh, I didn't think you were. No, maybe you were. Maybe there's a follow-up question to this, and maybe you could comment on as a student who's used both types of meters, or both types of displays. Actually, it comes down to the display and the reading of the display, right? Because you have an analog readout and you have a digital readout, not just thermometers, but you've used all kinds of different
In the labs?
yeah, types of meters, whether it be power, like watt meters, voltmeters, ammeters, some digital, some analog. Can you comment on the measurement technique that is used in reading a digital versus an analog, and how that might lead to inaccurate readings?
So you're asking me to clarify the process of reading each and then how it might lead to errors, or?
And how, yeah.
Okay. So for digital, if it's not calibrated, of course, that could be a source of error. Whereas reading the screen, it's kind of hard to. If you don't know your digits, you probably should be looking at the screen.
Right.
Whereas when you're dealing with divisions, or sorry, that's the first thing you want to do when you're dealing with an analog is define your divisions, and then you can kind of get a measure of. It's kind of in between these two. I'm going to call it 5, or it kind of depends on the actual size of the number it's between, of course, like the range of each of it.
Okay.
Yeah.
And so I agree with that. And so let's focus particularly on the analog now. Are there certain specifics that you should pay attention to when you're reading an analog scale to make sure that it is being interpreted correctly? Because I'm just wondering, because maybe if you had spoken about this a little bit, you could have justified your answer a little bit. So I'm just wondering if you could comment on that.
Could you repeat the question? Sorry.
Just if you're reading an analog, or when you're reading an analog scale, are there particular considerations that you should follow to make sure you get the correct value, so that the accuracy of the analog instrument is maximized?
You need to, obviously, like I mentioned before, figure out the divisions, but
Yeah,
also you
I think that's
might be dealing,
important. Yeah.
you might be dealing with two scales, 2 or 3 scales, in fact,
Okay.
on an analog meter. So you need to differentiate which one you're working on.
Right?
For example, the lab volt modules that we use, there were different plugins that dealt with different ranges of currents, and based on which one you were using, it would deflect a different amount.
Good, I think that's important too.
Yeah.
Is there anything else when reading an analog scale that would help you, that if you are someone who's reading an analog scale and you need to make sure the value can be very accurate on an analog
Right.
scale, if it's read correctly, is there anything else that you should do when reading an analog scale to make sure you're actually reading the correct value?
And put yourself in the lab and mention that.
There was a particular type of scale that we used that helped eliminate inaccurate readings. We use that in the fall term in rotating machines. Just wondering if you might comment on that and what inaccuracy could result if you're not using that type of scale, or if you're not very particular about how you read
You
the
said
scale.
we were using a scale in rotating machines in fall?
A very particular one, yes, which was an analog readout. I know Mr. Parker remembers because he just brought it up.
Okay.
I've done that 8 times.
Yeah.
I honestly cannot recall.
It was on a particular non-lab volt piece of equipment. It was a feedback EW604, actually, watt meter.
Oh,
Do you remember that one?
The mirrored scale?
What? Maybe you could talk about that and relate it to accuracy.
Well, the light of the actual, the arm of the measurement device is reflected off of the it's not backlit, I almost just said backlit.
No.
The reflective
Yeah.
backing, I could say.
Yeah.
And that gives you a very accurate reading right down, because it appears as if it's pressing right down to the actual, whereas most arms of measurement devices are slightly off.
Depending on,
So the needle that you're reading,
Right.
so what happens when you're reading an analog, so this is called a mirrored scale actually, right?
You can be viewing it from different angles, and you
Right.
could get a different measurement based on where you're standing in reference to the device.
Right, so in your case, I guess one thing you could have said here, right, was in regards to accuracy of analog compared to digital is what?
Depends how I look at it.
Depends on how you look at it, right? So if you're off by a considerable degree, not on center, right, but off center by a considerable degree, you have introduced inaccuracies in an accurate, right,
Yeah.
instrument
Right.
by reading it incorrectly, right? So most of the inaccuracies for analog instruments come from not reading the scale correctly, being off center.
Yeah.
And the mirrored scale actually prevents that, doesn't it?
Right.
And you notice that
Yeah.
in the lab.
I used it. Yeah.
Yeah. And I thought that was an important
That-
lab
that-
for that reason.
That hint helped me.
Okay?
I think that, you beat that one to death, but.
Well, just coming back a little bit to maybe on a similar topic
Yep.
is eliminating errors.
Right.
Can you tell me a little bit about your process of gathering data, and the fact that you have two panels, but I also noticed in your, I was looking through your documentation there, you were capturing data at the same time, right?
Yep.
So what was the purpose of that?
That was, well, generally when you're setting them up, you want them to have the same angle, so they have the same incident angle on their plate. You want them to be in the same, obviously, location, general location. The same air temperature climate around the actual modules is important. There's definitely one I'm missing, I just can't think.
So you're trying to make the test conditions
Exactly the same for the
Exactly.
two modules,
and
yeah.
that by doing that, okay, so again, that adds to the relativeness of each measurement from one body to another, right?
Yeah.
I'm sorry I couldn't really focus on your presentation there. I was trying to figure out some logistics here for the rest of the week here. But, so maybe I missed this. So you have one that was turbulent airflow, the other one was,
Laminar.
Laminar.
Linear, whatever you want to call it.
Yeah,
Linear
I
airflow.
don't know, yeah, I don't think it's laminar, but, how were you introducing the turbulence into your, in other words, what's the difference between the two panels physically to?
So physically, one of them has, and it's very hard to see, none of you in the audience could see it, there are bolts on it. They're also labeled underneath. I wouldn't lift them up, that'd be a mess.
Oh, that's all right.
But there are actual, the channels and the actual, which module it is labeled underneath in yellow tags. And the actual ribs, I can give you a photo of them too, one sec.
Sure. Because I was looking at your drawings, I couldn't really decipher.
Right. Well, it's hard with the 2D drawing of just the ribs to actually get a perfect.
Well, now I taught you how to do AutoCAD and 2D. I would not agree with that.
There's a photo.
Oh, okay, so there's
Along the top. So that helps to break up the boundary layer.
yeah. Okay. All right, so that, okay, that's what, again, I was missing here in the drawing. That's fine. Although I do, actually I see it here now that I know what I'm.
Yeah. That's what I mean, from two angles, it's just this thin little.
You could have labeled it, right?
Yeah.
Oh, it actually is, it says ribs right there, I just didn't see that. Could you bring up your, the schematic slide? You had a schematic there?
I didn't have an actual integrated, I had a working schematic in my PCB and the actual, but it's not integrated into the
That's fine, though, yeah.
presentation.
So you mentioned something about not having a ground.
Right.
Is that true?
I essentially have a circuit common where they're all linked together, and they run to the ground terminal of the DAC. However, it's connected through a USB to my computer, so it's really more of a bus bar.
So I guess that's what I wanna ask. Is there a distinction between ground and common?
Common is,
Maybe well, first of all, maybe I shouldn't have asked with using that term, but, okay, yeah, let's talk about that. So is there a distinction between ground and common?
circuit common would be just the connection point that they all share. So in your drawing schematic, you actually have circuit common, which is essentially a wire. That's how you represent it. Whereas ground is actually bringing it to the lowest potential point possible, which in a lot of buildings is an actual ground rod.
Do all circuits need a ground?
No.
No, you're right. Do they all need a common?
Well, I wouldn't imagine how it would turn. Like if you had just like a battery and a switch and you didn't have a connection for the actual elements, I don't.
Does it matter where your common is
Of course. Like you mean in a schematic or?
in a circuit?
Yeah, because you could have a short if it's in the wrong spot.
No, if you took a drawing there
Mm-hmm.
and you decided that taking out that symbology down for actually circuit common, which is what it is there,
Yeah.
and you drew a line there, could you make your common elsewhere in that circuit? Is there something stopping you from making it? In other words, take the two, what we traditionally call ground symbols,
Put a line.
and put a line across and get rid of those.
Mm-hmm.
Could you turn around and call anywhere else or any specific location on there, common, not ground, common?
My inclination would be to say no, but
Why?
well, because it's critical for the actual function of the elements.
Well, everything's there, put a piece of wire on the bottom there and get rid of the,
Yeah.
Very relevant.
Yeah, everything's relative.
Yeah, those two ground symbols are just showing that those 2 points are connected together.
Right.
So connect the points together, remove the ground symbols. Can you stick it up on the positive output of the LM35?
You're asking, can I link the diodes up to the
No.
positive?
No, because you took the ground symbols away, right?
Right.
They're gone.
They're just a wire now.
It's just a wire.
Right.
Can you stick the ground symbol up on the positive and be out there?
No.
Why not?
Well, these need to return to, well, for me, it's the DI110, it's the ground terminal. Like those two are a functional circuit, whereas these are essentially like a voltage measurement device, a meter almost coming into the circuit. So it's really just reading the potential developed across the resistor.
Good point, reading potential. So when we read potential, what do we have to read? From where do we have to take those measurements?
It needs to be with respect to a low point or 0 volts preferably.
Absolutely not. Absolutely not. If you want to read the voltage potential between the out there,
Mhm.
there is no, in this case here, you do not have to reference what is ground there right now.
Mhm.
What is the definition of a voltage, and when you measure it, what must you do? What's the definition of voltage?
Separation of charge leading to potential. Difference
Where?
across an element.
Across, meaning from point 1 to point 2.
Yeah.
None of that definition says
To ground or to
right,
0.
or to, right, to a common or whatever. When we are troubleshooting this,
Mhm.
and we want to measure plus VSS, right?
Mhm.
Where do you measure plus VSS? You've got two leads. Where do you measure plus VSS? Or VS, sorry.
What does it say?
I don't know where I got the extra S. Where do you read? 2 points, right?
Right.
Up top and,
Well, ground, like underneath here.
well, on the bottom, right?
Yeah.
Okay, on top and to the lower point.
Correct.
2 points. If you want to read the voltage across the two diodes, where do you read?
From the anode 1 to the cathode of the second.
No, across the two.
Across the two. Yeah. You
Oh, yes, sorry, yes, yeah.
Yeah.
I'm having a hard time.
Yeah.
Okay, yes, by all means, okay? So it's always 2 points.
Yeah.
We have the choice though of saying, I can start from a common point and read all over the place.
Right.
Or I can go across devices, okay?
Right.
So what makes that common point special? And why does it not have to be, for example, where your ground symbols are there? It's a trick question. What makes it special?
I know.
No, but what makes it special? It's a trick question. Nothing.
Is that
Nothing makes it special. If you chose to make your common point plus VS, or you chose to make your common point the positive output V out,
right?
all that means is that more than likely you are reading other voltages referenced from that point. If you were to make your common point plus VS, what would all your voltages be based on your knowledge of what you've read with the common point being?
Like if I was putting the meter around other parts of the circuit, well, I'd be getting 0 volts or a negative.
That's right, you'd be getting negative voltages.
Yeah.
And you'd be getting the negative voltage. What does the negative represent in those measurements? Potential,
Potential across the elements.
but what does the negative mean?
It's in the opposite polarity. It's
Exactly what it means.
Yeah.
It is below your common point voltage, that's all it means.
Right.
Okay? So, again, from my initial question being that you said that you didn't have grounds. Perhaps that's true, but you did have common points.
Right. Right.
Okay, and you just chose for that common point to be down there. In fact, you may not have noticed because you haven't seen what we've done in the past years or so, but we've moved away from using that symbology and many of the instructors to using the triangle symbology, which references no ground at all. It's a common point, a common return.
Right.
And not a ground, because that references a ground.
That's right.
Okay, and the reality is, I don't need a rod in the ground
Right, to collect
for
data.
this to work.
Yeah.
So why would I put the symbol to do that? You understand? So, for most cases, most instructors will just, or most people will blase over that, but when you start talking about, I don't have a ground, well, why are you using that symbol then? Because that's a symbol for ground.
This is the Texas Instruments data sheet.
Oh yeah, and I'm not saying they're not caught up yet, okay? But the movement is to say, let's have those symbols represent what they are,
Right.
and to even get away from the word ground
Right.
and say a common point or a common return, because that common point doesn't have to be there.
Right.
A quick example would be an old English sports car,
Yes.
which are known as positive ground, same battery, different reference point.
They tie the positive of the battery to the chassis, and they tie the rest of the system to the negative of the battery. Does it change anything? Absolutely not.
Do the electrons flow the other way?
Yes.
Yes,
We're over time, yeah.
thank you.
Good.
Okay, welcome to our second presentation of the day. Thanks again for attending NAV Canada, and for Jody and Dan too, good to see them here. So next up we have Hal Deep and his digital stopwatch. Take it away, Hal.
Thank you for a short introduction, Mr. Broad.
You're welcome.
Good morning, everyone. Grateful to have everybody here. I'm Hal Deep. I'm industrial control student option. I'm a returned student. Picking what I left off from last year, which is finishing my SBO project. And today I will present you my digital stopwatch. What will be included in my presentation would be the purpose of the project. I will include a little bit of history, context about the digital stopwatch, and yeah, it's about the stopwatch itself too. And the reason behind why I chose it, I spent for the last 6 months building it. And next thing is the functional overview. Functional overview is just based on everything on block diagram. It's just a simpler description how the project will actually work. And technical description is some of the deep dive into how the major components will actually build up the project. And complementary thing for the project is the testing, where help to determine what will be need to be improved for better function and trying to fix in the error that the project may have. And conclusion demonstration at the end of the presentation. Start up with the purpose of the project. I believe the stopwatch, well, in general, measuring the passage of time is, and using the man-made device is one of the, I would say, the best accomplishment of these modern human civilization. Back to 1776, if I'm not wrong, it's the first method was introduced how to measure the time. It's just a matter. It's just looking at the 2 point of the time, and like the watch is already invented at that time. So looking at 1 o'clock and 2 o'clock and 50 minutes and determine how much time that passed. It doesn't matter. And later into 1976, the first ever stopwatch was introduced in the sport events. It's a sport event, so probably it involved a lot of competition there. And most everybody, I think, will be familiar with the stopwatch that has the Victorian style, which looks like that one. It has the normally have 2 buttons. The button in the middle, usually you press it, and the needle would start counting the time, and either you release it or press it again, it will stop the timing. And the second button is usually used for the reset button, and we set the needle back to the neutral position. Nowadays, they do stopwatch and taking like many looking style, like which one I'm having right now is have the stopwatch function. Maybe in the handheld devices, or maybe integrated into your smartphone as well. Well, in my case, I use that for sport. I want to keep the rest interval time between my sets. I do the left way there, by the way. I'm trying to give the rest time consistent, and also do some isometric poll. That's something called. And I use that to mostly everybody. I think I use time instead in the kitchen, but I use stopwatch. Sometimes I cook a half-boiled eggs or a medium breast egg. And a little bit more about myself. I have ADHD syndrome, so what that means that my focus ability has been affected, and my perception of time is kind of different to everybody. Different by I mean it's kind of slower to everybody. I look at time, but sometimes, for example, I can look at a pen and not realizing that 50 minutes have passed without having any thought on my mind. So procrastinating is always my thing. Looking at a stopwatch, having it by myself can like bring me back to a reality that time not moving that slow as you thought. So, and lastly, I think physical logic has always been my favorite subject. So I want to do something based on it, using mostly just the ICs, flip-flop and everything like that. And because it's not sophisticated when compared to the MCU or microcontroller, so by that I mean the accuracy may not be achieved and reliable as using the MCU. But I would really want to know how far I can go with using a simpler components. Well, the function overview. Here I introduce you my block diagram. First, is the 6-volt battery supply. This is made up of like 4 plus AA battery cells acolyte. We just give it a 6-volt battery supply for the whole circuit, for the whole digital stopwatch. And second thing I want to mention is the clock circuit over here. The clock circuit, I mean, is a combination of the crystal oscillator with 2 other ICs. One of them is a 14 stages of division, and the other one is just a JK flip-flop. In this way, I want to build something that will give out the, not exactly, but roughly 1 Hz frequencies. The oscillator that I mentioned in the block right here is trying to get 1 Hz frequency, so then we simulate the each second passing by and use that to feed into something called 7-segment decoder. 7-segment decoder here. 7-segment decoder will take the signal from the 1 Hz frequency and convert it to the binary value that will fit into the 7-segment display. 7-segment module displays that segment numeric display. There are 4 7-segment coders that to represent the second and minutes. Because of my digital software that can count up to 99 minutes, I think I forgot to mention that. It has the resets and the start-stop function as well. Of course, it runs on batteries and I can turn it on and off. The decoder, there are 4 decoders here, and there are 4 7-segment display accordingly connected to it. The decoder cascaded, which means that the output signal of the previous one, when it's reached the limitation, will be the input for the following one. So the first one connected to the second one, the second one connected to the third one, and so on. But note that after the second one, the first one reaches limitation also connect, and this output also connected to something called limit increment counter that will limit the counting sequence of the second one to 6 only. That would probably make sense because it only count to 6 a second. Well, that's all you need to know about the overview of the function of the user software. Technical description, first thing I want to point out is the enclosure, the dimension right here, 17.2 times 8.6 for the Y and 3.9 for the height, centimeter or centimeter. The reason why I want to this enclosure is they have the battery holder built inside it, so that I don't need an external battery holder to put in it, and also it got the cover too, so it's probably to make it look better. And that's all I need to say about the enclosure, and here's the mechanical drawing. All of the major components are included inside the enclosure except for the switch, the on-off, start-stop, and reset button. One thing to say about it, the on-off switch was intended first to be the rocker button instead of just a slide switch. It's the same thing as the start-stop, but this was not carefully planned. Because the height of the enclosure is only 3.9 centimeters. When it put the PCB in, it take more than a half of the height already, so it couldn't fit in the rocker button anymore. So you can change it to the on-off switch, but it's still fine if I put a label on it so it's to recognize and tell them apart. And second thing, there are 2 standoff inside the enclosure already. They need to be taken out. I use the cutter to just cut them out. It's made of plastic, so it's easy to take them out, so that it can fit in the whole PCB bar inside it. That enclosure is the biggest one I can find, with the battery holder built inside it. Unfortunately, we couldn't find any bigger. Yeah. Second thing, for the technical description, PCB dimension 8.2 times 7.16. Before going any further, one thing I want to say is I want to thank you, Mr. Juha, as my advisor, and other 2 instructors, Mr. McCap and Mr. Jen, has spent a lot of time helping me design the PCB. It's my first time, same as everybody, but I got 21% of it. Imagine the amount of emails that are bombarded Mr. Juha. And mostly it's just for fixing the angle and the traces. As you can see here, the minimum traces in here are 12 mils, but only between the paths, and most of them are 15 mils. And there are some big traces in here that's 20 mils. It's for the sword, power, or switch, and it's what everything was so condensed. It was packed inside the PCB. So the first impression that instructors gave me that's better to survive because the pad was too small. Like, everything is relatively minimum. So when I do it drilling, of course I lift up some of the pads, but I managed to fix it by bending the pins of the IC into the trace and then solder it. Yeah, it survived. So, and schematic, I want to divide into the smaller sections so it can give you a better picture and help you get into more detail into it. So this is first thing that I mentioned in the clock diagram is the clock circuit. The clock circuit is built based on the crystal oscillator. The value of the oscillator is at 32.768 kilohertz. The reason why I choose that number because 32,768 is number 2 to the power of 15, which means if I want to get a 1 hertz frequency, I need to divide that number down by 2 for 15 times. So, and this is where the 4060 come here, U2. U2 is a 14 stages of 14 stages divider, which means that we're fit into the number 32,768 into it. It's already did 14 stages of division already. So then I need one more division, which did I do the U3 over there. It's only one IC, but it's divided into 2 sections. It's a dual JK flip-flop. The dual, what everybody knows, the JK flip-flop is mostly when you connect the J and K input into the logic 1. And the third input is a clock source fit into it. This will make the output toggle. So, which means that it makes the frequency divided by 2 for once again. So, because it's only react to the leading edge, like it's going tick, tick, tick. So it's only the leading edge only tick, and then not the falling edge. I got the frequency, the output of not exactly 1 hertz, but roughly around 1.28 to 1.46 hertz, depending on the temperature. Realizing that the colder it gets, and the frequency is get lower. And this is showing the images of connection between U4 and U5. I want to show how is the decoder are cascaded. So the clock pin over here, is the input pin was connected, taking the signal from the 1 hertz frequency via a switch, so then you can start a sequence. And when it's reached to 10, from the carry out pin right here, you feed into the input pin of the second decoder, which is U54026. And they have the pins to connect to the 7 segment. Accordingly to that, got some issue with ICAD when doing the PCB. Can clarify it out when I connecting that. Some of the pin from the decoder to the 7 segments have been, when converting from schematic to PCB, they've been mixed up. For example, it's the pin 10 connected to the pin 7 of the 7 segment. It's got to pin 9, for example. Yeah. And notice that from the decoder to the 7 segment display, there's no resistance needed. Since I found it in schematic, they already mentioned that they will sync the current going to the each pin of the 7 display down to 5 milliamps, so there would no resistance need. If, and another that when I connect to the resistor as well, the line is so dim, couldn't see it. Now, what about a picture of the whole schematic? The connection I just highlighted right here. The U14017 is the increment, the limit increment counter that it takes the signal from the first decoder. So this output decoder is not only connected to the U5, which is the second decoder, but also connected to the limit increment counter. So, and the output of the increment counter, U6, Q6 right here, which is only limit the increment only to 6 times. And the output is giving out going to the reset pin of the second one, which will reset it and connect it to the reset pin itself, which is when we read the signal, we will reset cell 2 and give out the signal will be the clock source for the third decoder, the 7-second decoder. And then it's just carry on the carry out pin to connect to the 4 7-second decoder. Second thing I highlighted right here is how I connected to connect the master resets of each decoder. They are all connected to the VDD via a switch. So when it press the button, it's close the switch and it connect the old resets pin to the VDD, and that will reset the old itself. And notice that between the resets pin of the U5, there's a diode over here. The diode will protect the reverse signal because it's not only connected to the VDD, but also is connected to the increment counter as well. So it will protect the signal. If not having it, it will start counting up to 6, or you cannot press a button to reset it half the time. Well, talking about the testing, first thing to mention about the accuracy test. The accuracy test will be done by using a secondary stopwatch to measure to see how accurate is it. The secondary stopwatch I use is my wristwatch, and notice that my digital stopwatch usually is count a little bit faster than the secondary device. So I will make it count first and it reaches 2 minutes, and then I will see how many seconds is lead compared to the second stopwatch. So recorded at the table over here. Oops. It's recorded at the table over here. First time it reaches 2 minutes, then the second device only 1 minute and 56 seconds, which is 4 second lead, and second time and third time it leads for more seconds. Probably I can. It's gonna be something to do with the calibration, of course. Maybe adjusting the value of the resistance, or it could be because there are many factors that could affect the counting sequence. One of them could be the battery too. Sometimes there's some of the batteries that here when 4 of them combined, they don't give a 6 volt, actually give 5.5 or 5.7, and give and that time I would use a new battery, and it could be more than 6 volt, and just increase the counting sequence as well. So, but overall, the average result was 91.39. And firstly, this was my intention was to let the digital stopwatch, my digital stopwatch would run up to 99 minutes, because you can go up to 99 minutes. But this was recommended by my advisor. There's no need to run it up to that, and run this at a lower value, and then you can time it. And the testing, the second test was conducted was the battery test. The battery test is just, I'm measuring the total current draw from my project, and then use the capacity of the battery then divide by that number to find out how many hours that this op watt could last on the combination of 4 battery in series. And the current draw with measure was 94 milliamps, and the capacity of the battery was 3,000 milliamp hours. Did some math, and it turns out the digital stopwatch would run 31 hours and 54 minutes. That's the value that really makes sense to me, because since the time that I left it running, I've been let it running like non-stop for a couple of days, and I see this can last for those hours roughly. Yeah, more than 1 day. Of course, depending on weather as well, depending on the temperature as well. And that's it. In conclusion, now before talking about the conclusion, there are some tests that have been done that I would like to mention. Is because mostly my project is run on the CMOS IC, so they are static sensitive, temperatures and moisture sensitive as well. So it could affect the count sequence pretty much. But that would be something I would look into the future to find out a way to test it, and in order to calibrate it and have a better result. So, and one more thing that I noticed, but I just kind of oversay, but I haven't found the answer. That when I leave my digital stopwatch near my laptop, the counting sequence start counting faster. That is something I couldn't explain. I had a video, and I can show it later. I also work as a backup for my demonstration as well. Yeah. But to conclude everything, is my digital stopwatch is a device can count up to 99 minutes. Not correctly, not accurately 99 minutes, but it can count. And as well with the reset function, stop, switch, and it's run on battery. I wish I can make something or I can put it in a pocket, but well, it's still, but need a bigger one. And so far, this has been many up and down during the project. It's how can I say, the element of surprise never failed to amaze me. On the day before the evaluation day, I failed to keep it off the ground. I dropped it on the floor. So I spent the whole sleepless night, but couldn't find it. It turned out it's just one of the pins of the oscillator for stove has been broken. I couldn't find it, even though I have a magnifying class. But very grateful that Mr. Chu had still gave me a very generous grade on that. But I managed to fix it. The one more thing that has happened to it as well is the 7-system display. They use, that's a reference. The U10, the C segment right here doesn't show, and I think there's a G segment of the U11 doesn't show either. This could be fixed by replacing the segment. Very simple, but I'm not going to risk it. I prefer to keep it that way, and I will fix it later because I want to give everyone the demonstration. But this kind of answers to think about if I really taking the segment out and then it doesn't work, and I'll show you guys the videos and kind of awkward doing the presentation day. And it bugs me all night. You can give me a hard time having a good sleep too. So that's it for the conclusion. I'm going to show you my reference already. Yeah. And now for the demonstration. Okay. Start turning. Yeah, as I mentioned, the C segment of U10 is missing and as well as U11. Start on. Start on the sequence. Then slower, stop it. Starting it. Oh, let us run to it 1-2 minutes. Here come the missing, yeah. Oh, I just realized I missed a label for the reset button. Oh, you dropped somewhere. Sorry. So, just a second. Stop it. Reset. And turn on now. Let's start again. Oops, no, not working. Now it doesn't do the same again. Stop it. Reset. Turn it on. Yep. And that's the end for my demonstration. I mean, I have something to show you too. This is the one that I mentioned. Oops.
Why do you need to show us a video of the same thing you just showed us?
I want to show you something that they can count more than just only single digits. And it's count up to 32 minutes already, and it's count a little bit faster than the one that I show you. That's placing really near my laptop. It's just my laptop is just above there, a couple 7 centimeters. Okay. And that's it for the demonstration.
Before you exit the demonstration portion here, can you show us what happens if the stopwatch is accumulating time and you turn it off?
Accumulating time,
Yeah.
turn it off, okay?
Yeah. What happens if you do that?
Okay.
Just curious.
Turn it on. Start time. Let it render a couple minutes, 1 second, turn it off, and still good.
So does it, so if you turn it off for 5 seconds, does it keep,
Okay, I can try.
what was it at, 17?
Yeah, 17, 18.
And then you turn it back on a few seconds later?
Yep.
So it actually pauses it?
Yeah.
Okay, just curious. Thank you.
Then,
Yeah.
okay. Blackout screen.
Will you bring up your schematic?
Oh, yeah. You mean the old one? The one that's showing everything?
Well,
Yeah.
could you just go back to that last one for a
Okay,
second?
yeah.
What does this slide represent here? You use it to represent something, and I'd like you to tell me what it represents.
Okay, just represent when connecting between the 4026 to the 77 is trying to say that it's limit the current. There is no resistance.
What
needed.
limits the current?
The characteristic of the 4026, it's just showing the calculation right here. And it's saying one of the characteristic of this 4026 is just the limit.
Where does it say that?
In the data sheet.
Oh, but you're saying this shows that. Where does it show that?
Right here.
But is that for a 7-segment LED display?
Yes.
No, it's not. Look at the symbology. You guys tend to ignore symbology. I love symbology. That has nothing to do with a LED-based display. In fact, look at the title on there. The first word on the title says it all. What's the title?
Tube deployment,
On top right-hand side there's a title to this drawing.
incandescent readout,
So what's an incandescent? What does that mean?
incandescent, light bulb.
It means light,
Light,
right?
light,
It's
yeah.
a filament, current-based filament.
Yes,
Are your LCD displays based on incandescent lighting?
no, sure.
So how does that prove, again, or justify you saying there's no requirement for,
So, I'm thinking, it's saying the characteristic of the 4026 at the BCC, which is a short put-in 6 volt, and given the current is minimum 5 milliamps. So, I'm assuming that the 5 milliamp is safe enough to put it in the 7 segment without needing any resistor.
well, that's 5 milliamps, but it's what voltage? 6 volts?
Yeah, 6
Minimum.
Minimum. It's the same voltage I put into.
So basically your 7 segment displays
Yes.
have 6 volts across the minimum with 5 milliamps through them.
6 volts is total voltage for the whole circuit. Yes.
What whole circuit?
For everything in here, then just powered up the IC and the 7 segment as well.
So, okay, so at VCC 6 volts.
Yes.
Then that's a horrible,
Yeah,
well, if you know, you shouldn't have used it. So it's what kind of, the output is what kind of output then? Is it a voltage-based output,
The voltage based output,
or is it a current-based output?
I think it's a current based output.
So how does it set the current? What happens if you have an LED that needed more than 5 milliamps? Maybe you want your LED display to be brighter. You want, so you have LEDs that can work at 20 milliamps, which is a typical number. How can you adjust this to make it 20 milliamps?
20 milliamps, so probably I would need to increase the voltage taken in because based on the DC.
Well, where does it say that?
We say order here, they say VCC 10 volt milliamps, and say IT, like that's not what I could read, but I think there's 7 or 8 milliamps. And then VCC 10 as well.
I think I'd like to see some graphs here, some calculations. This is
Uh,
not definitive. And for me, the big thing is it's basing itself on incandescent bulbs, so in your scenario, it's, no, I don't think it's rock solid that it's proving what point.
Yeah.
Why'd you pick 5 milliamps?
Why do I pick 5
Well,
milliamps?
you circled it, right? So it's 5, so your LED displays there
Mhm.
are working at 5 milliamps, I'm assuming?
Yes,
Is that what?
yeah.
Okay, so why did you pick that value? Because what else is tied to current?
So you mean why I picked this segment and run on 5 milliamps?
Yeah,
Okay. Actually, I just picked the common cattle 7 segment. So, and looking at the data sheet, and I assuming the 7 segments just had a limit of 25 milliamp maximum. So,
sure, but so what does that affect directly on your,
yeah, well, this which will affect because 5 milliamp becomes small, so the 7 segment could not show as bright as I need.
it wouldn't be as bright?
Yeah, so it would become bright.
So
as I
5
need.
milliamps, how much illumination did that provide you?
Well, just enough to see, but under other conditions, might not be enough.
Okay, so how again could you make this change so it would do that? That's what I'm asking.
Okay, so one thing I'm thinking about is increasing the voltage supply for it, the battery supply for it.
Okay.
We will increase the light, the illumination of the areas of the same segment, because I already tried that. I'm trying.
Did it work?
Yes, it's work. It's
So you tried
brighter.
that one in the prototype stage?
Yes.
On the board?
Yes.
So why don't you go ahead and do those changes?
Well, actually, I noticed that when I noticed that by accident. Actually, I let the prototype run on a 6-volt battery, 6-volt total, and it's bright. It's bright, and as you see in here.
How bright? Numbers.
How bright numbers?
Where would you find that information in? I'm not laughing at this, it's just a question.
It's bright that the one I'm showing you, but I don't have any value to show you. So
Where would you get those values?
the value of the voltage, or
Not the voltage, or the luminance of your,
I don't have any numeric or level of showing. I just say that because it's just brighter, and when the battery going to die, and it's just the illumination is getting dimmer.
oh, yeah, sure, okay, because you're going under those thresholds. But again, where would you get those values?
The value of illumination
Yeah, versus current.
versus current. I haven't really looked into it. I'm just assuming everything. So.
You know, this is assuming. Sorry.
No, it's all good. It's a good question. I missed the incandescence. It's a good point. Can you bring up the schematic, Bill?
Sure.
Let's go with the full one, yeah. Actually, can you go to the first part of the schematic, the first image you showed? It was zoomed in.
This one.
Yeah, that one there. I noticed the JK flip-flops,
Yeah.
they are the same number there, 4027, however, the symbology is different.
Yeah, the symbol.
Is there a reason for that?
It's just divided into 2 blocks, so that you can set more space, because it's 16 pins and it would be big like that, and so the symbol that the kind allow me to use is divided into 2.
I just mean the
Yes.
little triangle internal of the diagram. On the top portion is at C, the bottom portion is at J.
Yeah.
The top one has a Q and an inverse Q. The
Yeah.
bottom has a Q and an S.
Because it's a dual flip-flop, so we have 2 flip-flop here inside it.
Wouldn't
Yeah.
the flip-flops be the same?
The flip-flop, they are the same, but one of them I have to keep it neutral, and so that the other one to go up.
What does the triangle mean?
The triangle means is the, I think it's trying to show the clock, where trying to emphasize the clock is.
So what about U3A then?
Probably it's when I changing the number and the position of the pin, I didn't realize that the triangle was staying there. So
But
I
the
changed
triangle doesn't mean that, by the way, first of all. It means it's, the input is a transitional input. So it means it's either going low to high, high to low, that's where it affects it. Okay, so yeah, you should have, you moved things around and obviously didn't track that. But also the Q and S moving around and,
There's missing the inverse Q.
yeah.
Yeah, where's Q naught?
Cause I find it funny on the top one, you have R there, pin 12, that you don't use.
Yeah.
But then, S on U3A, it's not there, or it's not S, R,
Yeah.
or Q naught, that's the one, that's missing that you're obviously not using, it's disappeared there. You used the KeyCAD to do your
Yes.
design? Did you do a design, rules check?
Yes,
And did you get a whole bunch of pins not connected?
yes,
And what did you do for those?
I ignored.
You ignored it, yeah,
Yeah,
that's
I
the
ignored
way
it.
to do things, ignore it,
Yeah,
yeah.
I ignored.
Gives you good PCB designs that way, right?
Yeah.
Did you pursue as to why it was giving you those errors?
Just give me some warning, but I did a couple tests on it. I find it. It was the second one, the J and K, is left connected to the ground of the U3 grid, and the other been left floating. It could
So
be
what did you do?
It showed some warning in there, so, but I ignored it.
All right. Sure. I would recommend you not ignore warnings next time in PCB design.
Sure.
That way you might use less acetate.
Yeah.
You go in the next slide over.
Yeah. This one?
Yeah, this kind of applies to the same conversation Mr. Metcalf started earlier. But your 7-segment displays are U8 and U9. Is there something missing in between them? If they are LED based?
The pin 5 of the 7-segment?
No. Generally in an LED circuit, what parts do you need in an LED circuit?
Resistor, you mean?
Yeah. You should probably have,
Well, actually, there shouldn't be,
no?
but why shouldn't there be?
Because as I mentioned in the previous question, there's no need a resistor between the decoder and the 7-segment because it already sync the current.
Is that right?
It's already synced the current down to 5 milliamps.
So the resistor's not about sinking current. What's the resistor about? That's source and field. What's the resistor about? When we put a resistor in line with an LED,
Circuit current can run through it.
the LED needs a certain amount of current, but it also needs what across it. Can it handle 5 volts?
It's not going to be exactly 5 volt going into it.
I hope it's not gonna be 5 volts, not too many LEDs will survive that.
Yeah.
What's it gonna be though?
Is it going to be around 1.8 to 2.7 volt?
It's gonna be whatever the forward voltage drop of the diode is, depending on the color of the diode and technology, right?
Yeah.
Okay, so therefore, we have VCCs of 5 volts, we have VCCs of 3 point or whatever, right? They're always probably higher than what the LED needs. Okay? So typically, we put the resistor in there for a location to drop the voltage difference.
Yep.
Whose law?
Ohm's law?
Nope. Around the loop, voltage around the loop, whose law? Starts with a K.
Kershaw?
Yeah. Okay, how come here though, you don't need that? Those pins, A, B, C, D, E, F, G, what kind of characteristics do you have about supplying either voltage or current, and primarily current?
Yep.
You've identified that current, it has the current required, but if it provides the current required, what kind of output is that? Is it a constant voltage or constant current source?
I think it's not going to be constant, but because the signal can change the segment display, so some of the segment will not show, but let's say yeah, it's constant.
Well, which ones are going to be constant current or constant voltage?
Constant current.
It's going to be a constant current output,
Yes.
as opposed to a voltage source, which is constant voltage, right?
Yes.
So that's why the resistors are made, because it's supplying a current-based.
One last question?
Sure. Okay.
Can you go to your schematic, like the big picture?
Yep.
Yeah. Okay, or maybe the one that has U3B and U3A zoomed in. Sorry, this one is not great.
That's a big U4, U5, U6.
Yeah, this one here. So U3B, are you using that? Like, are you using the U3B anywhere?
Using
What's the purpose of U3B?
UCP, if they are the same at U3, you just divide into 2 blocks.
But I mean, the output of U3B doesn't go anywhere.
The outward, yeah, it doesn't go anywhere. I'm just gonna keep that to show that the second one must be connected to the ground so that the other one can work properly.
Okay, it must be connected to ground. So
Yeah.
what are, can you tell me what's the R and S and why the S is grounded and the R is not? These are important piece of that one. So you grounded the S, but not the R. The R is just loaded, right?
The R and S could be connected to the ground as well.
But what are they?
There are, because they are JK multi-stage flip-flop, so we have J and K input and S and R as well.
But what's the R? Like what's the terminology for R and S?
Set is for set and R is for reset. But when I'm connecting the R into the ground, can give me a very hard time to connect the
So-
PCB.
If I connected the S to 5 volts,
That would be the high signal, so.
what will happen to it? Doesn't matter if I have anything on the J or K. What will happen to the output if I have my S connected to 5 volts?
I may
Or
have to
six.
look back into the truth table for the JK flip-flop and display.
Like, I'm not sure why you're using, like, you connecting this and it doesn't go anywhere, like the output of it at least. Like, and you didn't like explain why.
I can make it not showing, but I just want to show if that one can be okay with it floating. This is the output.
Do you not need that for your PCB design?
No, I need that.
You didn't need that for your PCB design?
I only need the first one. The second one, no.
So that you could cut the chip in half and only put the first part of it in the design, ignore the other one?
No, not mean that way.
So you need both in your PCB design.
Yes, but one connected and one don't need it.
Okay, but here's the deal. This schematic is supposed to be a documentation schematic,
Yes,
showing the functionality of your circuit,
yes,
and not your PCB design portion of it. You're supposed to have two schematics. One you use for PCB design, one you use for explaining to us what's going on.
yeah.
So if you didn't have that there in the documentation schematic, this would be a lot clearer than us sitting there and going, why is he doing that? Why does he have that? Why has he got 4 mounting holes need to be grounded? Why is he, do you understand?
Yes.
Okay, good. Okay, welcome to, first, there's a lot of newcomers here, so welcome to the Senior Projects Symposium. And it is the third presentation of the day. And if you have to leave in the middle, the washrooms are out here in the hall, please use the back door, okay, to avoid disrupting the presentation. So up next, we have Justin Robichaud, and he will be demonstrating and presenting on his 3-story cargo elevator. Take it away, Justin.
All right, hi everybody. My name is Justin Robichaud. I'm in the industrial control class at NBCC, and for my SPL project, I decided to go design a 3-story cargo elevator just to kind of push myself to do a little bit more mechanical with my electronic portion of things, and also implement PLCs with all this. So the content that I want to talk about today about my project is like an introduction to why I choose this project and what brought out of it. A little bit of history too about like elevators, because elevators have not always been electrical elevators. In the past they were ran by other things or built differently. I'm going to go through my concept drawings as well, just to show kind of my thought process around the end too, and I'm going to try and talk to you guys a little bit like how it diverted from the original plans to what it is, because I actually ran through a few issues there while building it that I had to redesign more than once, which was a little hectic at points. I'm also going to present my diagram, my wiring diagram, my block diagram, just to show how the electronic portion of it works. I'm going to go through like the difficulties of what I had more in depth, give you the solutions I came up with them. Also going to talk about like how I could have made it better, or revision 2, what I could have done differently to even save cost or make it more efficient, because what we've been taught is every part you add can actually decrease efficiency, because everything has friction for movable parts anyway. And then my conclusion and references to where I got some of my information. So for my introduction, I choose the cargo elevator like I mentioned before because I wanted to do a PLC project, because I'm a big fan of PLC compared to micrologics and, or not micrologics, but microcontrollers. And I kind of wanted to push myself, because when I approached my advisor, he said, okay, what if I give you a legacy PLC, a Siemens S7200, and could you program it and make it run with that instead? It'll increase your knowledge on PLCs instead of just using the Allen Bradley stuff that we've been using in our classes. And I said, you know what, I'm down for the challenge. And it turns out I actually love Siemens a lot more than I thought it would. I did have difficulties though, because it's an older PLC, so, and it's also a different branch of PLCs too, so programming them is not necessarily all the same. Like for instance, Allen Bradley will go with rungs, Siemens will go with networks for the lines of coding that you're going to put in there, or the ladder logic you're going to put in there. And the purpose of my elevator too is to demonstrate kind of like a concept of cargo elevators, because in industries when you're going to bring a lot of cargo into different flooring, it's better to have something that could withstand a lot of weight to bring your stuff upstairs than taking the stairs, let's say with 300 pounds in your hands or back there. I wouldn't want to do that. And the features that I introduced with my elevator too is that a lot of doors will either open like sideways like this or up and down, but I decided I wanted to make something where the door opens forward as a little off-ramp, so that way that little seam that's in between the car and the flooring itself is basically just gone by that little ramp, so you could just push it right into it, and then it'd be a little easier, because I work at the hospital, and that's one of the issues we have with our elevators in the back for the cargo elevators, is the fact that when the door opens there's always a little gap, and elevators don't necessarily always stop directly where they're supposed to. There might be like a half an inch to an inch gap between the floor and the door itself, depending on if it's tuned or not or up to date. And that's something that gave us a lot of issues in the past. We're pushing it in or pulling it out, and either hear clink clunk because it would just get stuck or something. So a little bit of history too about the elevators is that the elevators have actually been here longer than people might think. They were there, basically made before even Jesus was born, so thousands of years ago, but they were typically when they were built back then, this is something I found online, so they were typically built with like man-powered, so men would like use mechanical aspects to make them go up or down, or even use animals, because at some points, I mean, if it's too heavy, there's only limitations that humans can actually perform. But they, during the like 1800s, that's when they were starting to implement more elevators that were more mechanical and stuff, that they were using steam to build up pressure to make elevators move up and down. And then around 1888, a German fellow by the name of Wiener von Siemens, I think I'm saying his name right, but I could be wrong, he built the first electrical elevator. But it only started getting implemented around 1889. But honestly, a little thing that I found amusing or fun is that the first person to invent an electrical elevator, his last name was Siemens, and that's what I ended up using as my PLC to run my elevators. I kind of thought it was a little funny in a way, but also there's different types of elevators when you go out into the world. You can have residential elevators, you can have cargo elevators, you can have commercial elevators. And there's different kinds. But these are like 3 different examples that I found online of like elevators you can get, where you can get a cargo where you see somebody there with like a dolly that just bringing cargo up the elevator to different floors. So cargo elevators are designed to withstand more weight than your typical residential elevator, let's say, where you're going to have thousands of kilograms of like product in there and you want it to be able to go up. Because one of the limitations with an elevator is that you have to fight against gravity pulling down that weight. And then you have the residential elevator that might support 2 people, let's say at most, because it's something you build in your house. You're not going to go build a big elevator that could bring up thousands of pounds or kilograms up there. And then you have the commercial that's typically 1 to like 20 people depending on where you go. The one at the hospital, for instance, like 1 to 25 people in that elevator maximum. Okay, so the concept of my design is that when I originally designed this is the final design that I came up with, for the fact that the original design, the cabin or the panel was actually shifted inside, so I could actually have all the handles vertically, but it was also bigger in length and width. The issue with that I came across is it wouldn't fit through the door. So I was thinking, okay, I have to compact everything and just make it fit through the door again. So I ended up redesigning the whole thing, making it more compact, pushing the panel to outside, because I was also thinking, if I put the handles in front of it, how can I open the panel if I need to troubleshoot? Okay, let's put it sideways. I can still carry it around even though they don't match the other side of the handles. The shaft itself for the elevator I had to actually make bigger because I needed to fit the alignment rods, which I used a 1/4 inch steel rod that I cut to 30 inches each just to align the car, so that way every time it moves up and down it doesn't go swinging left or right. I tried originally doing with 2 pulleys to save cost and weight, but the issue with that is that if you pull it and the weight inside the elevator is not equal, it'll start shifting a little bit on the sides, and you don't want it to go derailing if somebody's inside either. So I was able to do it with 3 pulleys on each side instead of 2 on each side. But the original design too, like you see this one, I actually forgot to add the counterweight because that was one of the last things I ended up putting onto my elevator itself. And the design of the counterweight is there to help ease the weight when it goes up and down, so the motor doesn't force as much when it wants to go bring the weight up. Because that was one of the issues that I found originally. Like this is the side concept there where the panel is, as you can see. I designed it with the car here, floor 1 here, floor 2 here, floor 3 here. And every floor has their call to floor button that brings it to the desired floor. So if you're on floor 3, you'd hit button 3 to bring it up to 3. They have open door buttons too, but those buttons you have to keep them pressed, so they have to keep energized for the door to keep opening, because as soon as you let go, it's going to stop. My idea behind that was that if the door opens and it doesn't align necessarily the same way as the other, you don't really want it to keep going and try to push up the elevator or push down, so that way you can align it yourself. And then there's a close button, that's the same thing. You have to keeping it pressed to close it, just in case. I left that one and that feature too, just in case that you'd ended up opening the door a little too much and you wanted to just drop it again. In the car itself, these two top buttons are unique compared to the rest of the elevator because they allow the user of the elevator to freeze any user interface outside of the car itself. So you'd open the door, get inside, okay, I'm using it, I don't want anybody to affect my work. The elevator is now non-available. You hit the button, anybody on any floors cannot do anything anymore until you decide to give them availability again. You close the door, pick your floor, go up and down. So this is a top view of my elevator. Again, it's missing the counterweight on top because it's something that was a last minute thing. But essentially, the original concept involved only using a motor, a cable, and the shaft. But the issue with that is I found that it wouldn't always work properly compared to using like a shaft or something to increase torque. Because I use a smaller sprocket on the motor and a bigger one on the shaft to try and increase torque when it rotates to try and help out the motor. Because I ended up getting a 1/4 horsepower motor, and turns out it wasn't strong enough. I was not expecting to make something too heavy, but it ended up being too heavy for the motor, too much of a big load for it. So I ended up putting the pulley that pulls on the cable on that shaft and just doing that concept. So this is the car itself, the design of the car. So the car it's designed in like two of the different pieces. You have the outer shell and then you have the walls. This is the outer shell. I left about an half, like all the measurements on this is a 1/2 inch measurement. And I put about 1/2 inch measurement on each side so that way I could mount the walls onto the main body of the elevator. And it's pretty straightforward, just a few holes screw on the sides because most of the stuff mounts on the sides. And then I have like the top screw here where the little hook goes on top, and then a secondary pulley for the counterweight to mount. So this is the wall concept, the side of the wall for the car. This one's has a little bit more holes. It's a little bit more mechanical or design, like hard to design, I guess, wise. Where you have your mounting screws on top here, but the original design again had 4 holes here to mount the pulleys because I was using 2 on each side. Ended up that 2 wasn't enough, but luckily enough, 2 screws is strong enough to hold each pulley in place. So I ended up putting one pulley that would go on top here, a pulley that go down here, and then another pulley going on top here because all the pulling forces on top, so I put all the pulleys upwards. And then for the 2 last holes, I just clogged them up there with a screw and a nut. And then on the bottom of the side, this applies to whichever direction you would have designed it, but essentially you make a 1/4 size hole to run your cables on the side just to make the door open with the actuator, because I made it run with an actuator. There's a contact switch in there, so if the door's open, the elevator will stay put. Nobody can make it move because you don't want it to stay open and then, oh, somebody called it up, it gets like jammed into the wall or something, and you wouldn't want that to happen. So this is my block diagram. It doesn't involve that many components compared to what I originally thought. It's more or less a lot of relays with PLCs and a power supply. So I start by getting 120 volts AC from the wall, converting it with a Rhino power supply that brings it down to 24 to 28 volts DC at a maximum current limit of 20 amps, which is implement current because at most, if I would run everything at once, I would run about 18 amps of current, but it's impossible to do that because if the door's open again, you can't make anything work and you can't make it jam that way. So then it goes to circuit protection, which I use a rule of thumb that my dad introduced to me when I was talking to him about it, is the fusing size you'd multiply by 1.25 to get something a little bigger, so that way if it actually does go to peak voltage, you don't end up ruining your fuse. So I have 3 different currents going to different branches, where I have one that's 3 amps, 5 amps, and 10. So for my 3 amps, I'm using a 4 amp fuse because I couldn't get a 3.75 amps, so I just got the nearest values for some of them just to make it work. And then for the 5, I was using an 8 because it's the closest size fuse that I had for the value, and then 15 for the 10 because again, closest one I had. So from the circuit protection, it goes to a block, terminal blocks. And then it splits to the PLC, the PWM that drives the motor, and then it also splits to a relay that controls the actuator. But all the controlling does actually happen with the PLC itself, because it is actually connected to every relay controlling everything depending on what button you would hit. So the 3 amps at 24 volts goes into the PLC, it goes into the push buttons, and then it also goes into one of the relays that controls the other sections of buttons that are outside the car. Because the car, no matter what, will always have the main functionality. It'll never be able to shut it off, because you'd want someone to have the main master controls. So then if the availability button activates, the relay turns on, giving supply to all the other buttons. Same thing applies with the contact sensor. I have the 3 amp source again going to the contact sensor, because I don't need a lot of current just to tell the PLC, okay, yeah, the door is open or closed. The proximity sensor is the same thing. I use a 3 amp source again, because only one proximity sensor at a time should be on, which there's 3 on the elevator. There's one on floor 1, one on floor 2, one on floor 3. And those, they look for the little metal pulley, because they're aligned with it, and every time it'll measure that pulley, it'll stop like desired floor. This is another reason why I was lucky enough that I could only use 3 pulleys, because if I would have had to use 4, I would have had to find another way to get that sensor to read another piece of metal, because if you'd go up and down, it would always get caught on the secondary wheel instead of the top one, right? So it wouldn't always align. So then I have the 5 amp source that goes into a relay. So the way the relay works, actually, it's like a little part, a little component that has 4 separate relays on it, and I'm using 2 of them because it has a maximum limit of 5 amps per relay that I'm using. And the 3 amp goes for the buttons, the 5 amp goes for the actuator. The 2 other ones I didn't end up using because they weren't strong enough for the PWM. This one ends up going to my directional relay, because I have 2 of those, one for the actuator and one for the motor. And what it is, it's a dual pull, dual throw relay that just shifts size whenever I want to go up or down, depending on the selection of floor that I picked, or if I open or close the door. And then the 10 amp source goes directly to the relay again, but this one, it's a solid state relay. It has a limitation of 12 amps, but I decided to go with a solid state because it was one of the best values that I could get at the time. Because during the pandemic era, the issue is a lot of parts started going out of stock, which is why I went with one that was solid state. It was a little more expensive, but it's the one that I could get that was still the cheapest for what I desired. So that's mounted, and every time it turns on, it takes that 10 amp 24 volt source and brings it to the PWM, turns it on, and then turns on the motor. Now the PLC, depending on which floor you hit and depending on which proximity sensor is on, it'll change the direction of the relay, changing the direction of the motor. So on a normally open contact for the dual pull dual throw relays, if it's open, it'll go counterclockwise, making it go up, and then it'll go clockwise when it's closed to go down. And for the actuator, if it's open, it'll make the door close, and if it's closed, it'll make the door open. I should have probably made them equal, be able to make it look a little better than one that's closed is open, but I mean, it works. So this is my wiring diagram. I actually went I tried to put the difficulty there, or the challenge there, to make it look exactly what it looks like in my panel itself. The only difference that I can actually say is the PWM is a little bit bigger, but it's also located on the bottom right corner. So I grounded everything in the cabinet, so the door's grounded, the sub-panel's grounded, the back of the panel is grounded, so that's where I get my ground source from too, to ground my power supply and my PLC. And then I get my neutral, and I wrote line, but I wanted to write live, I guess it's a typo, going to the Rhino power supply. And then from the power supply, it goes to this little section here, that I put a jumper across to energize all 3 fuses. And then from the 3 amp source, it powers the PLC, one of the relays on the 4-block relay. And then it also energizes the contact sensor, the proximity sensors. Then from the 5, again, it's just to show like it goes to the top dual pole dual throw relay, which controls the actuator. And then the 10 amp source goes to the solid state relay from the bottom side, that also controlled by the PLC because it doesn't need that whole 10 amps to turn on. And from there, it brings it to the PWM that takes whatever source. Because that PWM, the one thing that was nice is that you could adjust it for 12, 24, 36, and 48 volts. And depending on what you needed, it'll actually choose the current depending on what motor you actually attach to it. And then same thing, the dual pole, dual throw relay that just controls the direction of my motor. So the difficulties of this project is that, well, I took an electronics or industrial control. I didn't really take any mechanical courses or anything, and this project involved a lot of mechanical work. So when I originally had it all built up, after fixing the platform issue where it wouldn't fit through the door, I tried turning it on. The issue is the 1/4 horsepower with the PWM was running was not powerful enough to make the elevator go up or down. It would just stay there, and then it would go in fault to protect the circuits from trying to force itself too much. So this way it doesn't burn out, right? So then I ended up trying the portion with the shaft where I took a smaller sprocket and a bigger sprocket, trying to increase the torque from the motor onto the shaft and see if that would help. It helped a little bit, but it would only lift up about a few inches and then it would drop again. So then I stopped and I thought, I was like, okay, obviously my design is not the best design, but I still needed to work, so I still continued trying to push forward to make that design work, because at this point I don't have time to redesign the whole elevator by itself. So what's the best next step that I could do? Well, most elevators, if you look at how they're designed, they have a counterweight. That's something I did not account for, that I forgot to implement, honestly, onto my elevator. And so then I came up with the idea, okay, what if I make the counterweight go on the side, so that way when it goes up, it almost brings the elevator to a complete equal weight on each side from the weight and the elevator itself, the car. But I still made the car a little heavier, so that way gravity would pull it back down. But at the end, I made my design work with that counterweight, so that's how I solved that issue. The other issue that I can think of on top of my head is that even when I was starting to program the Siemens PLC, the S7200, it's an older generation of PLC. Honestly, I had issues making some of the features that we've learned with the Ellen Bradley work with this one because I wasn't very familiar with it. I got around it by reading the data sheet, but some of the stuff I had to think a little bit outside of the box to get some of the bits to work the same way, because there's some features like the one shot does not exist for that type of PLC. It's not there. I couldn't find it anyway if it does. So I just made rungs that as soon as the one bit energizes it, turns off that rung, or the network in this case, and it would move. Little things that I did just to help, right? So the cost of my elevator, I estimated about $2,000 when I first gave my concept idea to my advisor. I ended up wasting about $1,800 just making this concept. But then I was thinking, how could I save costs? Because willingly or not, it could have been cheaper if I didn't have to do all these extra steps at the end, because it wouldn't go up. So my revision 2 would have this type of concept there, where instead of having a separate shaft controlling everything, I designed my motor on top, and then have like a tension pulley or chain with a counterweight on the other side. That way when the motor moves counterclockwise or clockwise, they always keep rotating and I don't need that extra shaft. It's all one piece. Efficiency goes up. I don't have as much friction from other components into the build itself. And again, cost is cheaper this way. Less parts. Less parts is always better. So for my conclusion, what I loved about this project is the thinking outside the box, trying to figure out issues to problems that I don't necessarily have the answer for, because I've never really dove into them. But on the bright side, with everything I've learned from NBCC, I was still able to make the panel and everything work as I desired, because they give me enough knowledge to make it work as it does. And honestly, I would do that project again. I designed it revision 2, but I do not regret making that project. I gained so much knowledge just doing it. It was amazing, it was fun. And these are my reference sources from some of the information I got, so the pictures and so on the PowerPoint. And now I'm going to show you a small demonstration. But before that, I would actually like to show like the inside of the panel, to show you guys how I try to copy the wiring diagram a little bit. So as you can see, I have my power supply up there, my terminal blocks, fuses, the other terminal blocks, the center one, like the one next to the fuse blocks is another source, like 3 amp source. The one in the center is all my grounds, and then the other one on the side is just to get my outputs from my PLC to go through without making it look like the wires are going everywhere. It's just to make it look clean. And then I have my PLC on the top right corner, my solid state relay in the center, my PWM and the driver right in the bottom there, and then I have my dual poles, dual throw relays on the other side. So can everybody in the back see, or do you want me to try to figure out to put a camera in front and everybody can see? Okay, awesome. Okay. So my elevator is designed, again, that as soon as the power cycles, the first thing it'll try to do, if it's not in ground floors or level 1, it'll bring it back to 1, because 1 is its own. It's where it goes for safety reasons. Like if it has a brownout or something, when the power cycle is back on, it'll try to get itself back to level 1, and then it'll make everything back available on the buttons too, because the design is only a half door too. So if the elevator somehow loses power for just power outage or something, and somebody decides that they have enough being in that elevator and jumps out, well, there's nobody manning the elevator anymore. Once the power cycles back, it'll bring it back to 1, make everything available, so that way it doesn't get stuck on whatever floor it stopped. So right now it's on level 1. I'm going to show you guys what happens when I open the door. The only issue with opening the door at the moment is the actual actuator that I could get. It's either I could get one that was too big or too small. So I went with the too small to just demonstrate what happens when the door opens. That way, like, it's open right now, the contact switch is in an open state. I can't make it go to level 3, level 2, it stays there until I close the door. Now let's say I want to bring it to level 2, just hit the 2. It sees the proximity sensor stops. Level 3. Now the issue with level 3 is that's something else that was an issue of mine, is that I should have installed either a VFD so I could put a prohibitive mode in it, so that way the motor would stop and not keep moving. I did not account for any brakes or anything. I didn't really think about it at the moment itself of building in revision 1. So revision 2 would obviously have brake, because at the moment it just, as soon as it goes up, it just has that little bit of jerk and it just makes it move just a tiny bit off the proximity sensor. But let's say for instance that it would actually stay at floor 3. If I hit button 2, it brings it back down to floor 2, and then back to floor 1. So same thing here, if I make it not available for other floors too. Other floors cannot close the door, cannot open the door, cannot access the floors either, so no matter what you do, you cannot control it until the person inside the elevator itself decides, okay, I'm done with it, you can use it again, and then there you go, you get to use it again. So. I'm also going to demonstrate what happens if there's a brown up there. It just takes a few seconds for the power supply to de-energize in there. Capacitors are probably quite big in there if I'd open it up. I think this should be good. And then it brings it back to home. And that concludes my demonstration. All right, well, thank you for listening. I'll be waiting for the questions now.
I'll start. This isn't really a,
I can push this out of the way too there, so that way. Walking.
this isn't really a, this is more of a life pro tip than a technical question, but
Okay.
when you're in front of everybody, including your people that signed off on your proposal,
Yep.
don't ever use the words "ended up wasting money."
Yeah.
Fair point.
You use the money to do the research, and that's what it cost you to do the research, okay?
Okay. Note to self, I'll never use those words again.
Yeah.
Because you probably won't get a second project out of it if you use those words, right?
Okay.
Mr. Javert's in the room too, so.
Okay, now I'm nervous.
At the outset of your design,
Yeah.
what was your starting point? And I noticed you made a couple of observations that, well, it should have had a counterweight, well, probably need brakes.
Yeah.
Did you research elevators prior? Or did
When I
you
first made the design,
or did you start based on your PLC?
See, when I first did my design, I focused mainly on the PLC portion of things, and then because researching the PLC took a time by itself, just reading all the data sheet, because in my report I have over 200 pages that I had to go through just to try and get it, well, not necessarily 200 pages, but just to get it running. And then for the rest of the design, I kind of went off of like my experiences in elevators from work, and even the cargo elevator that's in A block, just trying to figure out, okay, so it does these features, but then I never really stop and think about it a little bit more than I should have, quite honestly, because I was mainly focusing on the electrical portion of the project, because that's where my specialty is, the electrical portion of it. And honestly, if I were doing this project in a team too, I would always request the help of a mechanical person, and instead of trying to figure out everything by myself, because at the end of the day, I wanted to work for my employer, and I don't want it to work janky or something. So I don't know everything at the end of the day. So getting help is never wrong.
Well, and I think that's a good comment, and to realize that, and also defend yourself a little bit in the workplace, that you're not a mechanical technologist, or so you're there for the electrical part and the electronics part, and then the rest of it, if they want to, they want to make that part work well. Yes, you can assist, but that shouldn't be your...
Exactly. I can give them a hand if they need to hold the wrenches or something. I can do that.
You can obviously learn from that, right?
Yeah.
You learn,
Exactly.
but yeah, no, that's something very often people forget, and that's where they get themselves in a bit of trouble liability-wise too, because they overextend their responsibilities.
Yeah, I think that is an important point to this project, and in projects like this, of this nature, is that there is quite a bit of mechanical aspect to this.
It's a lot more than I originally anticipated.
And the focus of, I mean, you took rotating machines, but the focus of that course was mainly on the electrical
Portion
part
of it.
of the machines, and obviously there was some mechanical, but it wasn't the main focus of the course.
No. So
Yeah.
I knew I could make the motor run for sure. It's just the rest of the stuff connecting to the motor, so it was a learning curve. It was very fun, honestly, but I would still seek out help no matter what.
Yeah.
So,
Mechanical issues aside, I think something that does apply to your studies, particularly studied PLCs, is that the first step in a good PLC design is a thorough understanding of the problem.
yeah,
A little bit of research into elevators at the outset probably would have been helpful.
probably would have helped a little bit, yeah, researching that at the same time.
You talked about fusing, and actually there's quite a bit of fusing in this. And you mentioned, I didn't write down what you said, but something about if the voltage goes too high. Can you explain what the fusing is actually there for?
Current
what does it-
limitation, not voltage. If I said voltage, I slipped up and said an ouchie on the presentation. No,
Is
it's
it limiting the current per se? Like, does it if the current in I think you have, what, a 5 amp fuse?
yeah.
Yeah, let's say the 5 amp protected circuit. Is it limiting the current such that if the current was to try to go beyond 5, it would hold it at 5? Is that what it's doing?
It'll stop it. It'll break the fuse inside and just cause an open and stop it from trying to damage any other components attached to it.
Right, so it's not so much current limiting where it holds it at 5 amps, or 5 amps plus your 1.25
0.25,
times
yeah.
1.25, like you said.
Yeah,
So it actually interrupts the current, right?
yeah.
Right.
So is error I did. I shouldn't have said increased voltage. Voltage doesn't have anything to do with the fuse.
Well, the fuse has a voltage rating.
So that way it doesn't
but-
arc
But the
across.
protection is based on current, isn't it?
Yeah, yeah.
What is the fuse protecting?
Well, the 4 amp fuse protects the PLC from getting any current that's higher than 4 amps in this case, because the maximum rated value for its current was 3 amps, and I didn't want it to try to get a 5 amp source or something going right through it if anything happens that I'm using too many sensors or it's trying to output more than it can and something fails in the circuit or something.
Which part of the PLC are you referring to in regards to the 5 amp fused
That one was
portion?
the 3 amp for the PLC.
Or 3 amp?
But I
So,
put it 4
so
amp.
which part of the PLC? Are you talking about the PLC's power supply line? Are you talking about the PLC's
I mean,
input circuitry, output circuitry? Which part are you referring to?
I'm referring to all three. So it's there to fuse the inputs, the outputs, and the power supply portion of it.
And which portion would most likely cause an overcurrent condition which would trip that fuse?
Most likely the input conditions, because I have about 16 buttons each, and I never really measured the current, and even to that, I don't really think it would necessarily get there, but it's just a precautionary measure just in case anything would happen.
Are you sure? Like, if you were to press one push button, how much current is going to flow into the respective PLC input?
It's supposed to be about 0.5 amps per input, but that's the maximum input, so I'm not 100% sure.
Are you sure?
the
500 milliamps for each button that you press?
So that's the
Are
thing.
you sure?
Because it says maximum rating, I don't know the amount it actually brings into it.
Maybe you're giving us the rating of the DC sensor supply on the PLC?
Could also be doing that. I was looking at it and I thought it was implying all the inputs, but it could have been implying only that one.
So how much current, so you close the call button here on floor 2, how much current actually flows in that PLC input?
At this moment, I would not know. I would have to go through the data sheets or even measure it with a tool or something to find out the exact value you're looking for.
What would limit it theoretically?
I would,
Yes, that's
I
a
would
good
just-
question. What would limit that current?
fair enough. I would actually go with the PLC but that's just on top of my head. That would limit it because it has circuitry built in that usually controls all that for us, so we don't actually have to worry about it.
What part of the PLC and what circuit are you referring to?
I don't know which part of the PLC itself, but I know it has its own like microcontroller in there that runs with the relays and runs with its own internal circuitry, so
Well, even if we simplify it down to Ohm's law,
then there'd be resistors in there controlling the
there's
current.
definitely an input resistance to each input on the PLC, isn't there?
Yeah, so the
Yeah.
only way is if there's a short on the
And
resistor.
as a PLC designer, if you were to design a PLC, what would you want the input resistance to be?
Well, honestly, I wouldn't want it to be high in the amp range just for sure, because it's only there to
Well,
control.
resistance is in ohms, not amps.
Yeah. Well, if I'm running 24 volts, can I take out a calculator?
No, you don't have to, I'm just, I'm
Okay.
not looking for exact
Well,
numbers.
I would assume in the thousands of ohms.
You'd want it quite high, right?
Yeah.
Probably even higher than that.
Yeah, just to limit all
Because
that.
do you want these inputs to draw a lot of current?
No,
No,
no.
right? You just,
They don't need to, right?
they
So
don't
why
need
would
to,
you?
you just want them to draw enough current to activate that input.
Yeah,
And it could be, I don't know, it's low milliamps, could even be hundreds of microamps. I do know that there was a project done last year that water was used to actually activate the inputs, and it functioned.
that's
And-
cool.
And there's not a lot of current flowing in that water, okay, so,
I can imagine.
yeah, all right, so,
Can I just,
yeah.
so if the inputs are relatively high impedance,
Mhm.
and they are the ones that are controlling the current, what is the likely device to cause overcurrent? I think you answered that, but I just want to.
Well, yeah, we want to go back to that now, yeah.
So what is the likely device that's going to cause the overcurrent?
Well, if the power supply ends up failing, causing more voltage going through it, it could increase.
Yeah, that's.
Because I
That's
don't
not-
know the
that's not
ratings of
likely.
the,
That's not likely.
Power supplies don't fail high voltage.
Because you had started saying that the inputs would be the source of high current, but I'm wondering if you might want to think about that a little bit more, because really come back to the same question.
I'm
Well, in
going
this
to
case-
what the fuses are protecting.
Right, that's what, yeah.
well, in this case, if they are limited with resistors, and the power supply is not to fail, the only other source that I could think about that would actually need the fuse is the power supply built into the PLC itself.
Now think about, you said what draws current, the PLC itself,
Yep,
the inputs draw a very small current, okay?
actually the outputs too.
Even if you had all 16, if I came up with my 16 fingers and
Yeah.
pushed all those input buttons, not much current's gonna flow,
No,
okay?
it's,
Two tentacles.
All right.
it's restricted, yeah.
So what's gonna draw lots of current that you need the
The-
protection for?
I'm gonna go with the outputs too, because the
Okay.
outputs are actually energizing other devices too, so
Yeah, and what are
But-
you, right? What's drawing current here?
the motor's drawing current, the relays are drawing current.
Are you driving the motor directly with the PLC output?
It'd be the PWM that's drawing the current. That's the ones that's controlling or driving the motor.
So what could happen now? What could happen on the output side that could cause excess current?
A short or something in one of the windings in the motor or something drawing too much current to try and,
It could be, I mean, you're driving some relays and things too, aren't you? And
yeah. So if one of the windings would actually have a short, creating even less resistance from it, maybe it would draw more than it can actually handle and create a fault or something that would draw more current.
a fault, something like that on the load side, right, on the output side, yeah?
Yeah.
Yeah, I don't know if you have anything else.
Well, again, for me, it's, again, so you've identified what could cause the failure.
Yeah,
So obviously the failure is gonna happen, right? Whether you have a fuse there or not, the failure's gonna happen, right?
It could, if it's not,
No, it's, the failure's gonna happen. For it to overcurrent, there has to be something that fails.
yeah,
So the failure, and it's more than likely either your load or, you know, whatever, okay? So it's not there to protect that, obviously, right? Okay. So, and we said that the power supply itself will not likely be
the issue.
the issue, okay? So what's left for the fuse to protect?
The only thing left for it to protect would be the outputs and then the devices. Could you repeat the
What else?
question?
What else? It's so obvious, but you guys always.
It's the nerves of being up front.
No, because I asked this question in classes too, and I have discussions on this all the time.
so if one of the relay coils fails as a dead short,
Mhm.
okay, what is the fuse there to protect?
Protect the other outputs because it would draw more current there.
No, it's gonna go through the coil, right? It's
Yeah.
path of least resistance. What else? Besides the fuses, the power supply, the coil, the input to the PLC, what is left?
The PWM, the relays.
I want to get a question into, so think of Mr. Metcalf's over in the other.
You had a nice diagram up there, right? What was on that diagram?
What kind of
You don't-
diagram
you-
was it?
It's a wiring diagram.
What kind of diagram again?
Wiring. Oh, you're okay. I see. It's protecting the wires from burning out.
Fuses
There
are
you go.
always there only to protect wires.
That's right.
Period.
Yeah.
Because the wires are in your walls or in your structures or whatever, and they are rated to a certain maximum current. And whatever other failure that can occur can exceed that current, and then what happens? They catch on fire. And then besides your PLC and your elevator not working,
Yeah, bigger
your
issues.
building burns down,
Yeah.
or your whatever, okay?
One more quick question, on
Okay.
the subject of fusing, I know we're at time, but when you're selecting fuses,
Yep.
let's say you give the example of you've got power supplies that run 3 amps or 5 amps or 10. Let's say you get a 5 amp power supply, you're selecting a fuse, would you, I like your dad's 25% safety margin,
Yep.
but would you select a fuse that allows it to run 25% overrated value or underrated value?
I would go overrated for the fact that if you go equal to it, if it ever actually goes to the 3 amp maximum rating, you potentially pop the
Okay, so
fuse.
your power supply burns up before your fuse fails?
A 10-cent fuse versus the $100 box.
And then
Fuse
under-
fails first.
Okay.
Fuse fails first.
Okay.
What you have to do is overrate your fuse, your wiring and everything, so that your expected loads are 80% typically,
Yeah.
okay? And then everything else is overrated by 80%. So then that means that if there is a failure, it's above what everything else, so there's no nuisance trips.
Yeah.
But at the same time, it will fail if there's a large failure.
Good.
I don't think it's anything fast.
I hope so.
Is that where you
Oh,
want?
I hope so. I really I would, yeah.
Okay, so the last presentation of the morning is by Yamju Lor, and she's going to be presenting on her automatic water level controller. Take it away, Yamju.
Thank you, Mr. Brown. So, today's presentation, I'm going to present about my SPR project with the automatic water level controller. My advisor is Mr. Juha, and I'm an electronic engineering technology student under the alternate energy stream. So before I start my presentation, I'm going to talk about the overview. So during this presentation, I'm going to talk about the background, like why I decided to do this project, the goals of this project, like the aim to the problems I want to solve, the principle of this project. We'll look also at the project functionality, like the concept diagram, the block diagram, and the schematic. I'm also going to talk about my PCB design and the test result that were done, the improvement to do on my project, and conclusion. I'll do some demonstration and then answer some questions. So look at the background. So the major problem people face in my hometown is about the water availability. So most of the system used in my hometown is the mechanized pump, which is attached on the borehole. This system is this system is not as great as my project because it requires more physical labor to be done to actually have the water coming through the hole, and also some people may not have accessibility to use this system, like some seniors who doesn't have enough strength, and also people that also have handicaps. So this is an image of the mechanized pump, and also type of system used is the manually controlled pump, electrical pump. So this system is used as the pump is manually turned on and off. So, and the third reason I wanted to talk about is also the power outage, which is also like a main problem faced by people in my hometown. Due to this problem, the manually electrical pump is not as great because some people we not have access to water every time due to the power outage. So the goal I want to solve is make sure people can access the water anytime. To also avoid flooding of the water. I also want to save power and also to save money too. So I'm going to explain like the working principle of my project. So the main component used in my project is the NE555 timer, which is the main component that controls the starting of the point, the start and stop of the pump. So my project is to make the pump turn on when the water level in the tank is at its lowest level, and then turn off when it reaches its highest level. So the first thing we're going to see is the concept diagram. So this is an overview on how my project is supposed to look like. So on this side we have the overhead tank, and which is used also as a storage tank for future use. And we have the underground tank, which is used as a simulation of the underground water. So the underground tank is just as reference because I cannot do it. I cannot put the pump on the ground. So and we have the overhead tank that will store the water, and we also have my controller. We have the 4 LEDs which represent the 4 different levels in the tank. So look at the block diagram. So my project is powered by 4 sets of batteries. So the 2 sets is used to power the IC, and the other set of battery is used to power the relay. So when the IC is powered by the first 5-volt battery, and if the water in the tank is below its minimum level, this will send signals to the relay switch, which is a normally open relay. Then the relay switch will close so that the signal goes to the water pump, and then the water pump will start running until it reaches the maximum level of the tank. And we have this the 4 levels represent the different level of the tank. So as the water increases, the LED will illuminate and show the level of the water in the tank. The next thing we see is the schematic diagram. So the schematic diagram has so these 4 blocks are the terminal blocks I use on my PCB. And has the 4 sensors connected to it. The other part, we have the diode, which will protect the IC from the back voltage. And then we have the normally open relay, which is connected to with the use of the terminal block is connected to the pump. So we have the R12, R3, R5, and R11 are used to protect the LED from current. And we have and the principle is that when the 5-volt is supplied to the IC, this will pin 2 will send okay, when the power is going to the IC, pin 6 will be the voltage across pin 6 will be 0. So when this will trigger the IC to send the signal to the relay, and then the relay will close, and then the pump will start working until it reaches the highest sensor. Then the voltage across pin 2, which is the trigger, we trigger the IC to make sure the relay opens, and then the pump will stop. So we move on to the PCB design. So during this project, I think the PCB design was the hardest part during my the design of my project. So I had no knowledge about PCB. So this was the first time, and the trace width I use here is a 15 mil, and the part size, the round part size is 80 mil, and then I also found the placement of component really tricky because because you have to bring to close component beside each other to reduce their roughness. So, and I came up, even this one is still have one arrow on it. You can see the trace going to the other part. It's not in the middle, so yeah. So I'm going to talk about the test and result. The two tests I performed was the battery life test and the LED visibility test. The first test I did was the battery life test. So for this test I used a multimeter to measure the load current going through my IC unit and the relay and water pump unit. So as you can see, the load current going to the IC unit was 167 milliamp, and the load current going through my water pump was 124 milliamp. So with this formula, I did some calculation, and I came out with the number of hours if the system is used non-stop. The second test I did was the LED visibility test. So for this test, I used the light meter to measure the illuminance of the LED. So to do this test, I use I was required to use a dark room with no light coming from the outside. So the first, the ambient light is the loss I measure when there's the light coming from the outdoor, and then the second one I did was with the light coming in the room, like everything was open. So by that I did the differential. I subtract the illuminated light from the ambient light to get the actual loss of my LED. So the next thing I'm going to talk about is some improvement that's supposed to be done to make my project better. So the first thing I omit to include in my project was a switch so that I can easily turn on and off the system without actually have to unplug the battery from it. And the second thing I also omit to include is an indicator for the water pump so that the client or customer can easily identify if the pump is on or is off. So we go to the conclusion. So some application where my project can be used. It can be used in restaurants, even in school, where you want to automatically supply water, and the main advice or thing I learned from doing this designing of this project is the attention to detail. I think that was my main problem, because if I was really attentive to my details, I would have come with a fully working project with my PCB. So unfortunately, I could not use my PCB because I did the wrong negative. I gave the wrong PCB, which I did not include the negative part. So, and I could not get the voltage going for my PCB. And the also second thing the advice I will give, also a lot of troubleshooting should be done, even though your project is not working. You have to know where the problem comes from to be able to do better or improve your project, your design. So during this design, the initial cost I had when I was starting was $100. So and then the I only used $84.40 for this project. So this is my reference for the pictures that I used during this presentation. So before I go to the demonstration, I just want to let you know I'm not using my PCB, like I said, because it wasn't working. And the second thing is that I accidentally destroyed my pump because I set a high voltage on it. So I will just show you the display part where the LEDs, and I'll explain how it was supposed to work with the PCB and the pump. So these are the sensors I use for this project. Normally the sensor is supposed to be immersed in the tank, but since I don't have the pump anymore, and I just wanted to at least do a demonstration so that you guys can at least see how my project is supposed to function. So we have the LED display here to show the level of water in the tank. I'm not too sure if you guys can hear the relay when it clicks, but so right now when the water level in the tank is at its lowest level, which is the 25%, the pump will start running. Like right now the relay is now closed. So when the water increases in the tank and it reaches the highest level, the relay will open so that the water will stop working. So yeah. This is all for my presentation.
Thank you. Can we start with the schematic?
Sure.
Bring up the schematic, please. Let's start at the right-hand side of the schematic where the motor is. This pump, if the pump is running,
Yeah.
what I'm trying to figure out how does, is it K1 that's controlling power flow to the pump?
Yeah.
The
So
K,
really-
the K1 contact?
Yes.
So
On the diagram I have, yeah, terminals 2 and 3, right? Is that what's showing up there? It's hard to see, that's all, yeah. So terminals 2 and 3. So what happens, can you explain to me what happens in this, the way this is drawn, when K1 is energized and therefore the contact connecting terminals 2 and 3 closes?
So when
What happens?
When the contact closes, then the pump will energize the pump so that the pump starts.
let's look
Really?
at this electrically here.
Really?
Let's do an electrical analysis of this. Let's just not jump to that conclusion just yet.
Yeah, like,
So when K1 closes, tell me how does the motor get energized at a circuits level? You have a circuit there for your motor, right?
Mhm.
There has to be current flowing through it for it to turn. So where does the current come from and where does it go? What's the source and what's the
Yeah.
return for that motor?
The relay.
so let's say that K1 is energized and terminal 2 and 3 are connected together, right? That's what happens here in this diagram, okay? What is the relationship between the 5-volt rail and ground 2? I see you have, well, that's another question. What's the relationship between 5 volts and ground when the K1 contact closes? Electrically, what do we call that?
What type of circuit?
I don't remember.
So let's follow it through. Start at the 5-volt. You see where I mean? Just above and to the right of the K1 contact.
Mhm.
There's 5 volts there. That's a supply voltage, right?
Yeah.
And just below there is a ground. It's marked ground GND2, right?
Mhm.
So let's say that K1 contact is closed. I want you to follow the current path from 5 volts through the K1 contact. Where do you end up? But your lips moved, but I didn't hear anything.
No, I.
You're gonna need to say it eventually.
It goes through the pin one of the pump.
No.
Well, why would it go there?
No, yeah,
Why would it go there?
but I want her to explain what happens with the switch. What happens when the switch K1 or the relay contact K1 closes? Where is the current going to flow?
Mm.
Start at the 5-volt rail, 5 volts there, and where does it go when the switch closes? Where's the current go?
To the right.
To,
The right.
well, that's where you want it to go, but it's not gonna go there here. Why not? You want it to go to the right, you want it to flow through the motor, through the pump, right? And cause the pump to turn on, but it's not gonna happen here, is it?
When a switch is closed, what electrical circuit does it form?
what's the resistance of a closed switch?
What's the resistance?
Yeah.
I've measured the resistance, but I don't recall the.
Well, I mean, just, you took circuits, right?
Mm.
What's the resistance of a closed switch? If you're going in the lab, you go in the lab, remember in the first year lab, you had those little knife switches? You open the switch and you close it. If you put your ohm meter across the switch and you close it, what's the ohm meter measure?
Is it overload?
Well, okay, it's either gonna measure OL or it's gonna measure something else.
It is the something else.
What's the something else? Let's get the two choices down. There's two choices. We'll narrow it down to two choices for you. The OL, what's that mean on an ohm meter? What's it mean?
Overload.
No, what's it mean though? What does the OL mean?
Physically in the circuit.
Yeah.
Open
The circuit has a name.
Open
yeah.
circuit, right? It means open. Okay? So it's either going to measure as open, a switch is going to either measure as open, or it's going to measure as closed, which is equal to how many ohms? Because the OL means open. But what's the other measurement you're going to get? So that kind of gives it away. The open switch measures as an open OL, right? So when you close the switch, what does it measure on the ohm meter? Ideally.
When you touch the two leads together.
Oh, zero.
Zero, right? So the closed switch is 0 ohms, okay? So now what do we have? K1 and the pump motor form what kind of circuit?
Close.
Well, no, like series or parallel.
Oh. Zero.
How many points in common are shared between
Oh.
the parallel? Where does most of the current flow in a parallel circuit? Which branch? The one with lesser resistance or the one with more?
More.
Most of the current flows in more resistance?
No. Less.
Most of the current is going to flow in the path of the least resistance, right? So you close K1. Where does most of the current go? We could argue all of it, actually.
To the hole.
Hmm? Where does the current flow if you close K1?
To the relay.
Through the closed relay contact. How much current does the pump motor see? If all of it flows through the contact?
Zero.
0. So this won't work. This circuit will not work. Not the way you wanted it to. You didn't want to build a circuit that essentially shorts the power supply, right? I know you said that you had some issues. Maybe that's part of it. I don't know if you hooked it up like this or not, but if you hooked it up like this, every time that the relay would energize, the power supply would get shorted out. And it would actually de-energize the pump would never energize because you're shorting the pump out. You're shorting the power supply and the pump out. Okay? Right? So that's a major problem here. So I don't know if she had it hooked up that way or not, but, yeah.
If K1 is open, the pump is tied
Yeah.
to the source directly.
Technically, yeah, it would. Technically, it would run when the relay is open, but as soon as the relay closes for the first time, is there any fusing here anywhere?
No, what's that?
So maybe, maybe the failures that you were having was because of a poor design. Not maybe, 100% sure, probably, you know, okay.
Can we?
I was gonna ask another question here, but
What?
I don't wanna hog it. But the thing is it might be hard to ask because the circuit's wrong.
I know, that's what I was.
So anyway, maybe you have another question you wanna ask.
Well, okay. Can you tell me your sensors, or you showed a video there of your sensors. What type of sensors are they? How do they work?
There are float sensors.
So they're float sensors. So basically when the water hits them, they mechanically close a contact.
Yeah, when the water hits it, it goes off.
Okay, so my question then therefore is, what's the purpose of the 555 timer then? 'Cause it's obviously not a timer. What does that do in your circuit? So when one of your float sensors turns on, I'm assuming.
Can I point out too that the reason why he's having to ask that question is it's not the correct symbology for a float or a level switch, right? So,
So what's the purpose of your 555 timer?
Is to send the voltage.
Oh, voltage goes somewhere? What's voltage? Voltage is something you measure between 2 points, right? So it can't go anywhere. So restate your answer using proper terminology here.
So the sensor will. What was your question again, sorry?
What's the purpose of your 555 timer in your circuit? When one of your float sensors closes or opens, I don't know, again, I'm really unsure here of what it's supposed to do. You said that your motor was supposed to turn on at 25%. So which sensor would that be?
Sensor one.
So when sensor one opens or closes? Opens? When the water level goes below 25%,
Yeah,
does the sensor open or close?
open.
Okay, so it opens. So what happens to the 555 timer then? What happens to the 555 timer? Why do you need a 555 timer? Why not just hook all that to your coil K1 there? Assuming everything would be wired correctly, your motor would start running.
Because I wanted the pump to start when the sensor is open.
Okay,
When the sensor closes, when the fourth sensor closes, then the pump stops.
which one?
The fourth sensor,
The full?
the fourth.
Okay, so how does the 555 allow that to happen?
Because the voltage going the voltage going through the IC
The
divides.
voltage doesn't go through things, we just stated that. Voltage exists between 2 points, okay? Okay, so you can't tell me that voltage goes anywhere, you're breaking so many rules of physics.
So when the power goes to the IC,
The power, okay. So, let's talk about voltage applied to pins instead, okay? So, which voltage is applied to which pin?
it's applied to pin. The V plus I.
The non-inverting? Is that what we're- So pin 8, well that's 5 volts, it's applied to there all the time,
Mhm.
from your source up top, okay? So what happens then? Okay, I'm trying to understand what that IC is doing there. How is it turning on the motor and,
Okay, so the voltage goes to pin 8. The
it doesn't go, voltage doesn't go. Stop saying it's going, it's, okay? It's applied to pin 8, okay? So you have voltage applied to pin 8 from your VCC.
Then because there is 2 flip-flop in the IC, so it will divide the voltage going to the pin 2 and the pin 2, pin 6 and pin 3. So
Pin 2,
pin
pin
six.
6,
and pin
and what was the last one?
3. Pin
3? 3 is the output.
yes sir.
Okay, so what happens?
So when the applied voltage on pin 2 is 1, I think 1.
It's on 1, it's how much voltage? It's a voltage, 1, you mean binary 1, is that what you're, or it's 1 volt?
No, 1 volt.
Okay, 1 volt,
No, I said when the applied voltage on pin 2 is 1/3
oh, 1/3, sorry, yeah, okay.
of the supply voltage. The
Do you have the internals of the 555? You don't have a schematic with the internals of the 555? That would help you explain this.
yeah, I had it on my report too.
Okay, maybe we should have added here too. All right, so it applies 1/3 to TR, which is trigger. What else?
And the pin 3 too. So
And pin 3 what, sorry?
the voltage is pin 2 and pin 3, which is the
What happens to pin 3?
when the voltage is applied on pin 8, the flip-flop in the IC divides the voltage going to pin 2 and pin 3.
So the voltage at pin 2, is that not supplied by the sensor through, across the sensor, right? Is there 5 volts across your sensors applied across the common to pin 2, right? That's what you're telling me, I'm assuming. And then what happens at pin 3? Pin 3 is an output, right? So what gets applied at pin 3?
What gets supplied?
Well, what voltage can I measure at pin 3? Tell me at pin 2, I'm at 1/3 of the voltage coming in or being applied to a V plus. So what would I expect to see at pin 3 to the common?
One third of the voltage.
1/3? is that gonna be enough to open your relay, or close your relay? But yet, I want the relay to close, because if it was configured right, I want the motor to run, wouldn't I? I think that's, you gotta look into that, okay? You need to understand how that works inside. Okay? Inside that 555, because that's kind of the key to this whole thing.
I have a follow-up question in regards to K1 contact. I guess voltage doesn't go anywhere, but she managed to make it disappear here. But where would you put that K1 contact, knowing now that it is in the wrong place? Where would you relocate it to?
Because I want the voltage, I want the, because I know the second 5 volt is in the wrong spot.
That's not the second 5 volts, that's the wrong spot, it's your contact for K2.
Yeah, K2, pins 2 and 3 there, K1, I think it is.
K1.
K1. You identified in the last round of questions before Mr. Metcalf's that it's in the wrong spot, okay? Because it shorts out the power supply when it's closed. So where would you move it to such that it would be correctly positioned in this circuit?
Connected to the pump. Most of it is connected to the pump.
Where though? Explain where would you put it in the circuit? Because there are several ways that I could connect that switch to the pump, but there's only one correct way. Okay, so tell me how would you position that switch or that relay contact K1 so that it would be correctly inserted in the circuit?
Let's show your virtual pointer there. You can show us maybe where you would.
So, I'll connect the pin 3 and 2 to pin 1 and 2 of the pump.
Oh, you'd move it there? Would that solve the problem? If you moved the switch along and connected it between pins 1 and 2?
Because I want a common ground for my relay and the pump.
What do you want the switch to do? That relay contact, what is it supposed to do? Don't talk about commons or anything, just tell me what you want the switch to do.
To energize the pump.
You want it to energize and de-energize the pump by doing what? What is the switch doing to make the pump, cause the pump to be energized or de-energized?
What does switch need to do? I think.
From a circuit's perspective, what is it doing then? Or what do you want, not as it is there, but what do you want it to do?
Just switch.
Yeah, what do you want it to do? Control what about the pump?
Voltage.
The,
Voltage.
you want to control the current, right? You want to make the current, the pump current, whatever its full value is, or you want to make the pump current 0, right? So to do that, what relationship does the switch have to have with the pump?
Being serious.
It has to be in series. So I want you to tell me, how would you wire K1 in series with the pump? Where would you put it?
I'll connect the pin 3 in series with pin 1.
You would connect pin 3 where?
In series with pin 1.
So show me with your mouse pointer where you would put pin 3.
Here.
Right there. And where would you put pin 2? There. So you got pin 3 correct. Where would you put pin 2? Or terminal 2? I guess time's up. Okay. Thank you.
Thank you.
Johnny, I took it back.
Okay. Welcome back to the SPL Symposium. For this afternoon, we'll have 2 more presentations. And it's good to see many of you who joined us earlier today and earlier in the week, that you're back again. We like to see that. And so this afternoon we have Jordan Burke, and he's going to present on his PV irrigation system. Take it away, Jordan.
Good afternoon, everyone. My name is Jordan Burke, as Mr. Broad had said. I am an expecting graduate of the Alternate Energy Systems program here at NBCC Moncton, and today I'm going to be talking about my senior project, which is the PV irrigation system that I designed and installed at a small community garden about 30 minutes away from here. So, the structure that today's presentation will follow is as follows. I'll begin by giving a brief overview of the system by reviewing the concept drawing and block diagrams. I will cover the background on the project location where the actual system was installed. I will be reviewing my system components by showing pictures and giving some specification information for all my components. And then I will review my project testing I performed on the project and follow up with some final thoughts. So, for my system overview, we have my block diagram here, which, as you can see, the main power source for my system is a PV array up here. That PV array is connected through a rapid disconnect switch to provide safety for, access for firemen to disconnect these from the system. Those PV panels are then fed through a PV combiner box with internal circuit breakers. That combined output from the combiner box then leads to the charge controller, which serves multiple functions in this system, one being to provide charge current to our battery bank, and the second function being to control our load, which is a 24-volt diaphragm pump, which will provide the water pressure for our system. On the intake of our pump, we have a low pressure system here, which consists of a pond that is located uphill from the site. This pond then fills water reservoirs, and these water reservoirs are connected to a low pressure manifold, which feeds our pump. On the outlet side of our pump, we will have a high pressure manifold and our irrigation hoses. All of the electrical components for this system will all be located inside of a small pump house on the garden property. So, this shows my major concept drawing for the project. The upper view here shows the aerial layout of the garden, which shows the rough dimensions of the garden as well as approximate locations for the 2 water reservoirs, the pump house, as well as the low pressure manifolds and the high pressure manifold. The lower view here, the outside pump house view, shows the rough dimensions of the shed that the system will be located inside, and it also shows the PV panels mounted on the roof. These panels were mounted flush to the roof, as the roof had an approximate 30-degree slope, and the practice for mounting summer use panels like these is to reduce the mount angle by 15 degrees from your latitude, which the latitude for this site is 45 degrees, so that 30-degree angle worked out perfectly for these panels. In between our panels, we have our disconnect switch, which has our electrical conduit, which carries the PV wire and the bonding wire into the shed. Our back wall view here shows the rough dimensions and layout of the components inside, featuring our combiner box with the PV panels running into them. The combined output from the combiner box goes to our charge controller, which feeds our battery bank through a battery disconnect switch, and then the pump is also controlled by the charge controller. So now that I've given a brief background on a brief information on how this project works and some of the components, where will this project be located exactly? So, the Garden of Salem is a community garden that's located in Hillsborough, New Brunswick, and was started in 2013 as an initiative of the Hillsborough Baptist Church, as you can see here. This garden serves to provide a place for community members to grow food, as well as provide an inclusive atmosphere for everybody in the community. On top of all of this, they want to remain environmentally friendly. So the site currently features a roughly 27,000 square foot garden outlined here in red on the church property. And that garden is enclosed entirely in deer fence, like you can see here. This area is prone to, local wildlife, deer, rabbits, stuff like that. So this fence helps keep those animals out so that they don't destroy the crops in the summer. This site also features a pre-existing watering system, which I had mentioned earlier in my block diagram. It's a low-pressure system that is fed by a large pond uphill from the site. This pond then gravity fills large water reservoirs, 1,000-liter reservoirs. There's one here, and there's one on the opposite end of the garden behind the pump house here. On the outlet of those water reservoirs is a 4-valve manifold, which community members use to fill watering jugs, and then they would, manually water the garden by walking around. This kind of presents the issue for this system with being inclusive for everybody in the community. If you want to have young children involved, or maybe people with mobility issues, having heavy watering jugs that they're always carrying around, it's not really going to be ergonomic for those kind of people. So it was decided that a pump-assisted system with a high-pressure manifold, as shown on the right here, the left here, would be added to the system. This manifold holds 4 outlet hoses, which are fitted with our spray nozzles, as you see on the right. All community members have to do to use the system is grab a hose, turn the valve, and water the garden. From there, they can just turn off the valve and leave the hose for the next person to use. Now that we've covered the background of the location of the system and some of the features of the garden, I'll review our wiring diagram. So, our 2 PV panels are routed through a disconnect switch as seen here. This is a 4-pole single throw switch, so you just turn the switch and all the panels are disconnected. From there, the panels are connected through our PV combiner box, which has 2 internal circuit breakers as shown here. There's also a 3rd circuit breaker that we added in just as a kind of a backup in case any of the other 2 happen to fail catastrophically or something like that. This combiner box also has a grounding bus, which provides all of the electrical grounding for our system, including bonding the PV panels, the frames of the panels to the ground, and a negatively common grounded battery. The ground for the system is provided by 2 ground rods, as you can see down here, which have been connected to the system using 6 AWG stranded copper wire. From the output of our combiner box, we have our charge controller, which, as I mentioned earlier, serves to regulate the charge current that's provided to our batteries, as well as power the load, which here is shown up here as our pump. Speaking of the pump has been fused with a 10 amp inline fuse in order to protect the wiring for the pump. The batteries have been protected by a terminal block fuse down here, and also a rapid disconnect switch has been featured for the batteries as well, just to provide disconnect access for maintenance and troubleshooting purposes. In between our 2 batteries, you can see a small temperature sensor which is connected to our charge controller. This serves to regulate the charging parameters of the controller based on the temperature of the batteries. So, what would this system cost approximately if you were to build it out of pocket? Well, down here you can see, it's pretty small, but the total system cost, if you were to buy all the components yourself, would be roughly $3,700. It's an expensive system, mainly due to the fact that the batteries cost about $800 a piece. They're quite large batteries, so they really account for most of the system cost. Thankfully, the cost of the system turned out to be much lower because the batteries, the PV panels, and the charge controller were all generously provided by our electrical engineering technology department. The total system cost without these components would be roughly $1,100. So you can see that the batteries and the PV panels roughly account for 70% of the system cost. So here we have some pictures of the finished build. We have our pump house shown here. This was provided by the students of the carpentry class at the Caledonia Regional High School. They built this last year, and I guess they had one left over that they couldn't get rid of, so this is what we had decided upon. It was originally going to be that we would use a steel-sided shed, but apparently on the day that the steel shed was going to be installed, a big gust of wind picked it up and took it across the garden, shredding it to pieces, so that didn't work out so well. On the upper right picture here, you can see our PV array. It's a 2-panel array, and our disconnect switch is located in between the panels. The conduit runs along the underside of the eave of the roof and goes into the back wall of the system, or of the pump house, sorry. Down here you can see our component internal view, showing the conduit running inside from the PV panels into our combiner box, which features our internal circuit breakers. The combiner box is then fed to our charge controller, which is then routed to our batteries and our pump. The inlet of the pump can be shown down here, and the outlet of the pump is here, fitted with a pressure gauge. So you can't really talk about a PV system without getting into the array. It's really the main face of the system. It's something that everybody kind of recognizes as being a solar system. So the array for this system is a 2-panel array, and it consists of 2 CSUN 260-60P polycrystalline solar panels. Under standard test conditions, these panels can output a maximum power of 260 watts each, which results in a maximum array power of 520 watts. The max power occurs at a voltage of 30.3 volts and a current of 8.58 amps. So this results in an approximate parallel array result of 30.3 volts and 17.16 amps of total max power current. These panels have been connected through a rapid DC isolator, as shown here. This DC isolator has been included for CEC requirements mainly. It's required if the combiner box for the system is located more than 1 meter away from the array. This is basically just for firemen in case they have to disconnect the panels from the system in case of a fire. The switch comes fitted with attached MC4 connectors to make easy connections to the panels and to the extensions. The bottom right picture here shows our combiner box face. It's a pretty plain gray panel, and on the inside we have our internal circuit breakers. As you can see, the 2 circuit breakers on the left are the ones that are actually being used in the system, and we have 1 extra one here, which is just for backup. The PV panel frames were bonded with 6 AWG copper wire, the same as what I've mentioned for the what had been used for the grounding rods. So the PV array installation was done with help from 2 of our wonderful instructors here, Mr. Broad and Mr. Pert. They helped by installing the extra roof joists to get the panels mounted securely to the roof, and kind of just help get everything set up and get some holes drilled for the panels and whatnot. Most of the work on the roof was done by myself, and everything was done safely using fall arrest gear. You can't really see it too well there, but there's a little yellow fall arrest harness there, and I'm hooked up to a nice anchor on the other end. So the charge controller for our system is the main control part of our system, really. This charge controller is an Ever Tracer Series Model 4210, and it regulates the power provided from the PV panels as well as controls the load in various ways. This charge controller it can function on both 12 volts or 24 volts nominal voltage, and it will automatically sense and adjust the system accordingly, depending on what battery bank you hook up. The maximum charging current for the batteries is a 40 amps maximum charge current, and the discharge current that you can receive from the batteries is also 40 amps. On the PV side of things, the maximum voltage that you can have for PV input is 92 volts, which works out pretty well for myself because my PV is only 30.3 volts max power. So that worked out. The maximum power that the charge controller can handle from the PV panels is 1,040 watts when used on the 24 volt setting. This is about double the capabilities of what my panels will output, so I think that works out well as well. As far as load control, this charge controller has multiple options inside. You can either just have on-off load control using the the enter button here. You can set it up with a timer that is based on the sunrise, so when the sun rises you can have the load turn on for a set amount of time, or when the sun sets you can have the load turn on for a set amount of time. So yeah, it offers some pretty good freedom for the load. This charge controller, as I mentioned earlier, also offers temperature adjusted charging through a temperature sensor connected near the batteries. This charge controller also has the function of connecting to a PC via a RS485 to USB connector, and you can download the associated software for your system, and you can monitor things like the different parameters of the system. You can alter charging parameters for the batteries, and also it has a full programmable timer inside the software as well, so that you can control the load to turn on and off at any time of day that you want. The battery bank for the system consists of two 8G, 8D power surge batteries. They are gelled electrolyte batteries. They have a 12 volt nominal voltage, obviously, and the current capacity of these batteries is 225 amp hours. So these batteries have been connected in series to create a bank with a nominal voltage of 24 volts and a current capacity matching one battery of 225 amp hours. These batteries have been protected by multiple means, one being the battery terminal fuse, which is shown here. It was the best option that I found for the system just because it connected directly to the battery bank, and they recommended that the fusing be connected as close to the bank as possible. Another protective method in the battery circuit is the disconnect switch, as shown here. This also has lockout capabilities, so that when you're working on the system, you can either just remove this key entirely from the switch so that it can't be turned, or you can just lock it out so people can't get access to it. So for the irrigation for my system, this is the pump that I used. It's a relatively small pump, but it provides some pretty good output as far as I'm concerned. It's a C-Flow 42 series pump. It's a positive displacement diaphragm pump, which runs on 24 volts nominal voltage, just like the rest of our system, and it draws a maximum current of 7 amps when running. The output capabilities of this pump are a flow rate of 5 gallons per minute and a pressure of a maximum system pressure of 55 psi. One thing I'd like to mention is this pump features an internal pressure regulated switch, which when the system when the output valves of the system are closed, when the system pressure reaches that 55 psi mark, the pump will automatically shut off. And then when the valves are reopened on the system, the pressure drops to about 41 psi, and then the pump will turn back on. This, makes it so the pump doesn't draw nearly as much current as if it were running constantly. This pump has also been protected using a 10 amp fuse, which is an ATO style fuse, just an automotive fuse. I thought this was the best for the system just because it was the leads on the fuse were also the same as the pump, and these are just readily available anywhere and easily replaceable. So I mentioned system grounding earlier and that it was provided entirely by our combiner box's ground bus. What I didn't say is that the grounding rods for the system are actually 10 feet tall. So here it shows a picture of me next to the grounding rods. And let me just say, you don't really realize how long 10 feet is until you got a sledgehammer in your hand and you spend 2 hours driving one of these things into the ground. So for the second grounding rod, we decided that would be a good idea to get like a demolition hammer, like a jackhammer, and like the associated driver bit, and use that to install the second rod so that it didn't take nearly as much time. or pain on the hands. So here I just have a brief video of the second ground rod installation. This has been sped up 4 times, but really the whole installation was about 2.5 minutes from start to finish.
And you didn't like the sledgehammer.
That's a little better.
Yep, saved my hands quite a lot of pain the week after that.
That was pretty slippery. Now we went to, yeah.
So, now that we've covered all the main system components that went into this system, I'd like to talk about some of the testing that I performed on the system. The first one that I performed was a battery capacity test to make sure that the system would run for an appropriate amount of time if the PV panels weren't receiving appropriate insulation from the sun. So, for my calculation on the right here, I assumed a 50% maximum depth of discharge for the batteries just to keep a safe limit. And the pump was going to run for approximately 2 hours each day. That was kind of a maximum limit that I had estimated. And it will draw 7 amps of current. So this would result in an approximate system autonomy time of 8 days, which I think for an area like this, we don't ever really get an 8-day stretch where it's just constantly cloudy. And if it does, then it's likely raining. So this system is probably not going to be really necessary. But yeah, an 8-day system autonomy time would result in approximately 16 hours of total pump runtime. So I wanted to make sure that the batteries would be able to supply this for that amount of time. To perform this test, I first disconnected the PV panels from the system entirely so they weren't providing any charge current to the system. I attached a single hose to the outlet of the pump, and I fed that hose back into the water reservoir just to not waste any water. I turned the pump on and I left it to run for approximately 2 hours, taking measurements periodically of the battery bank voltage and the current that's being drawn by the load. So this here shows the results of my battery capacity test. I used the results of the current and the voltage that I measured to calculate the total energy consumed by the pump over the 2 hours. Then I used that to calculate the estimated capacity that would be remaining in the batteries after that time. So from my 2 hours of test results, I came up with this graph, which shows the battery bank capacity dropped from roughly 225 amp hours to approximately 217 amp hours. But since this system, I had estimated that it would run for approximately 16 hours, I thought that this wasn't quite enough of a showing of the system's capabilities. So using the trend line in my graph, I produced an extrapolated trend line for a 16-hour period. And at the end of the 16 hours, I saw that the battery capacity remaining was approximately 157 amp hours. So this results in the following calculation, which shows that the state of charge remaining in the batteries after these 16 hours was approximately 70%. I thought this was perfect, as it didn't really even come close to the 50% depth of discharge limit that I was hoping to keep in this test. My second test that I performed was to determine the water flow output of the pump. I wanted to make sure that it was kind of outputting what we were expecting, 5 gallons per minute. But yeah, I performed this test by just putting an open-ended hose into a big 5-gallon water jug like you'd see on a water cooler. I opened the end of the hose, I timed it with a stopwatch, and then I recorded the amount of time that it took to fill the entire 5-gallon jug. Using those times, I calculated the approximate amount of gallons that would be transferred in that 1 minute that the pump was running. And after my 5 tests, I came out with an average of approximately 3.84 gallons per minute for the pump's output. This may have been low because some of the fittings on the outlet side of the pump may have kind of been restricting the flow, the pressure sensor, and there were some step downs in the size of the the outlet system, so that may have resulted in the loss of flow. It didn't really affect the output, the water output of the system, however. It seemed that the system worked quite well with this amount of flow. A third test that I performed on the system was just a simple test to determine the pressure when various amount of valves were open on the system. I was doing this basically just to see whether the pump would, shut off at its correct pressure and kind of turn back on at its 40 psi pressure. So with the valves all closed, the system resting pressure was sitting at approximately 50 psi. This is a bit lower than the 55 psi limit that we were expecting, but this might be due to the pump has a small calibration dial that you can change the exact pressure at which the pump will shut off. So it may have been slightly miscalibrated when when we received it. When one valve was open, it consumed it put out an output pressure of approximately 35 psi. This also resulted in a 6.1 amp current draw for the pump, and the visible flow from the single hose that was open was quite good. For two hoses, the output pressure was approximately 20 psi, which lowered the current draw to approximately 4.8 amps, and the visible flow from the two hoses was still quite good as well. With 3 or 4 valves open, however, the pressure seemed to drop, quite close to zero. Obviously, it's an open-ended pump now. There's no pressure in the system. The current draw didn't drop that much, from 4.8 to only about 4.2. So the flow from 4 hoses at one time really wasn't sufficient for what I had seen. Like the water kind of just started to trickle out of the hoses rather than actually give a good spray. So from this test, I kind of concluded that the system would be best used with 2 valves open at any time, because this would keep the water flow well, and it would also reduce the amount of current consumed by the pump, and thus the amount of energy consumed. And so now that I've discussed my project and the testing results for my project, what are some of my closing thoughts? Well, first of all, the project results. I think it turned out really well. I don't know how well I expected that small pump to work in the system. I thought that maybe it wasn't going to output nearly as much water as it would. It was quite a strong pump for just a little small pump like that. As far as my budget, my initial project budget I had assumed for the project was about $2,000. This basically, the reason that the final cost was so much more was the batteries I had initially chosen for my design were much smaller, and the PV panels were also a less expensive, much smaller PV panel. Some of the things that I took away from this project, well, the first one is definitely the value of time management. I know you've probably heard it plenty of times, but the #1 resource we have here is time. And yeah, I lost a bit of time there towards the end of the design process, about 3 weeks, due to some personal issues, and having stuff prepared well in advance was definitely helpful for getting back into it and kind of making it an easy entry back into the project. A second takeaway that I would take away from this would be the complexity of a PV system and like how much more difficult it is to install than I had initially thought. Like the fact that the grounding rods had to be installed 10 feet into the ground, the amount of work that went into installing the PV panels on the roof, it really was quite a lot more than I had anticipated. And what are some of my recommendations for the future of the project? Well, Mr. Broad and I had discussed maybe adding additional electrical loads to the system, so like maybe lighting inside the pump house or even outside the pump house to like let people see there at night. There could be another pump added in the future down the line on the other water reservoir to provide another pressurized manifold for even more freedom of watering. In order to do this, it would definitely be required that there would be a load bus added to the charge controller's load output. It would definitely add a little bit more to the project, but it would make it easier to add all of these additional loads to the system. And another recommendation I would have would be to maybe put the batteries into some kind of battery cabinet or something, just to give them a little bit of extra protection from the elements, and in case the pump does happen to have a leak, there's not water spilling out over onto my batteries. And yeah, that's pretty much what I got for the presentation. And as much as I would want to bring all of you down to the garden to give a demonstration, I don't think it's practical to drive 30 minutes there, do a 5-minute demonstration, 30 minutes back. So I prepared a short 5-minute demonstration video just to give kind of a brief overview of the system. Hi there. Today I'm here at the Garden of Salem in Hillsborough, New Brunswick, and I'm going to be given a demonstration of the PV irrigation system that I designed as my senior project. So here we are outside the pump house of the garden. Up above me here you see the PV panels and the disconnect switch between them to disconnect the PV panels from the system quickly. The conduit running along the edge of the shed roof runs into the shed and provides power to the rest of the system. So now, I'll take you inside the pump house to show you more of the components that lie inside. So here we are inside the pump house. Along the back wall here, we have our conduit running in from outside, which brings our PV wiring as well as the bonding wire for the PV panels into our combiner box. The positive poles of each of the PV panels are connected through a circuit breaker internal to the combiner box, and then the combined output is fed to our charge controller. This charge controller, as you can see, has many different monitoring functions, such as functions to monitor PV panel voltage, PV panel output current, battery voltage, battery current, as well as load current and load energy consumption, as well as many others. This charge controller also has timing functions for the load, such as turning on the load when the when the sun rises, or turning on the load when the sun sets, as well as a full comprehensive programmable timer to turn the load on at any time necessary. Now, to power our load, when we don't have any sunlight, we have our battery bank. This battery bank consists of two 12-volt batteries wired in series to create a 24-volt bank with a 225 amp-hour capacity. These batteries are protected by multiple methods, one being a battery terminal fuse with a rating of 75 amps, as well as our battery disconnect switch, which provides easy disconnect access for maintenance and other purposes. Finally, in the system, we have our water pump. Now, this water pump is able to output a maximum output flow of 5 gallons per minute with a maximum pressure of 55 psi. This pump on the inlet side comes equipped with a mesh strainer in order to clean the water before it goes through the pump. And on the outlet side is connected to a pressure gauge to monitor the pressure in the system in order to ensure that it is always at the correct pressure of approximately 50 to 55 psi. So here I am beneath one of our 2 water reservoirs. These water reservoirs are filled with water from a pond that is located uphill from the site, with water being gravity fed through hoses in order to fill up these reservoirs. Prior to the installation of the pump system, community members used these reservoirs to fill up watering jugs, just like this one. They would then use those watering jugs to walk around the garden and water the plants manually. In order to make the gardening experience more inclusive for everybody in the community, this high-pressure manifold was added. All community members have to do in order to water the garden is turn on one of our 4 valves, grab the hose with the attached spray nozzle, and water the garden, just like they would at their own home. When they are finished watering the garden, they can simply turn the hose off, return it to its position, turn the valve off, and the system is ready to go for the next person. So I want to thank everybody for watching this video, and I hope that it helps to understand the function of this system and give a good demonstration of how it works. Now, all that's left to do is close up our pump house door so that members of the garden don't have access to the electrical system inside. And so that concludes my demonstration, and I'd like to open up the floor to our panel of instructors for any questions.
Jordan, if the sun's shining full blast and the pump's running,
Yep.
are you still drawing from the batteries?
No, if the sun is at its full power that it's being able to output, the panels should provide more than enough current to the charge controller to be able to power the load, as well as provide extra charge current to the batteries.
What is the full output of the sun?
1,000 watts per meter squared.
And how much of that power can the panels absorb?
The panels output an approximate max power of 260 watts apiece, which I think from the data sheet, the panel efficiency was approximately 16%.
Yeah.
So they may have been using some slightly different maximum value for the sun.
Can I just ask you to reiterate
Yeah.
just a second? He asked you, what was your specific question?
It started with how much power can we get from the sun, and then how much.
And that's where.
Okay, yeah.
And you answered,
1,000 watts per meter squared?
is that power?
No.
What is it?
That-
It's a good answer to give,
Yeah.
but what is it? It's not power, it's what?
Energy?
No, it's watts. But it's watts per meter squared, so what does it become instead of power?
That is our power density.
What's another name for it, do you know?
I can't remember off the top of my head.
Insulation, right?
Okay, yep, I did say that at the.
But I much prefer power density too, because it tells me right away, it's a per area, right? So good answer, just not really what he was asking
Okay.
technically, right?
It was a trick question.
Yeah.
That was, yeah.
Sorry.
While we're on the subject of units, okay, again, this thing, again, just to slip, we've seen this happen before. You talked about your panels providing 30-ish volts of, and I quote, power.
Oh. I misspoke there pretty hard then.
Yeah.
30.3 volts of our maximum panel voltage.
And then there was you corrected yourself actually on the next sentence. I don't have it written down there, but on the next sentence you did say voltage, and okay, so, but I just caught
I noticed that too. I thought he meant at maximum power.
Oh,
That's what I thought he meant,
okay.
maybe, but anyway, maybe he didn't mean that. Okay, no, you go ahead.
Just a quick one, there was a couple of terms in there, I'm not an alternate energy guy,
Okay,
I want you to say it one time. What's PV?
photovoltaics.
What was DOA? I know DOD, SOC. what's
That is days of autonomy. So
Days of autonomy,
basically
thank
how many days the system can run.
Would bear a little clarification.
Okay, yeah.
Not dead on arrival.
Acronym.
Can you finish the sentence, the number of days that the system can run, ...
Without PV power.
Yeah,
So without the sun providing ample
What?
insulation.
Yes.
why two ground rods?
That was actually recommended by the Canadian Electrical Code. One of the main things for grounding conductors was that if you were using prefabricated grounding rods, that two were necessary, and they were to be located approximately 3 meters apart.
Thank you.
Yeah.
Go ahead. Don't be shy.
So your your configuration, basically you're using your PV to charge the batteries,
Essentially,
and then
yes.
the batteries will feed the load.
The charge controller handles all those functions internally. It can either provide power directly from the PV panels to the load, or it can provide charge current to the batteries. And if the panels aren't giving enough current to power the load, then it will draw off the batteries.
In addition,
If
right?
if the PV can provide enough current to the load, then you're gonna charge the battery.
If the PV panels can't provide enough current to the load, then the batteries will be drawn off of to power the load.
But are they gonna be charged? Like,
They're
you have
not,
some
they're not
supply-
going to be charged during that time, no.
Then where the energy is gonna go?
It,
Coming from the PV
it goes directly from the PV panels to our load,
to the load.
yes.
So some of the energy comes from the battery and some the other one.
Yes, that would be essentially how it works. It's drawing from the two sources simultaneously.
Okay, let's say that your batteries are full and your both PV are like generating at full capacity.
Yep.
Are we gonna cover the load and we have some, or is it gonna cover the load and we don't have any energy or power?
From the specifications of the panels,
Like what's the load size you have
the load will draw approximately 7 amps of maximum current
at 24 volts?
at 24 volts, yes.
That will,
It's approximately just under 200 watts of power for the pump.
and each PV can generate 260.
Up to 260 watts, yes.
So you'd have at least 260 extra.
Yes.
Where is it gonna go? If the battery is full.
The charge controller will actually limit the amount of current that is being provided from the panels. So, like, if the panels are outputting, say, 10 amps of current, and the batteries don't need to be charged, it will regulate that down to about 0.1 amps, just as kind of a trickle current, to be able to keep the batteries charged, rather than, you know, just dumping a whole bunch of excess current into the batteries.
But they still have some energy coming from the PV.
So what's happening to that solar energy?
It would be
I don't
consumed
think
by the
it's,
charge
in
controller.
reality, it wouldn't happen for that location. But what do you suggest? Like if I have an extra energy and I need to.
But it's not, because what it does is
He's supposed to answer that.
No,
No, what happens to
maybe
the
my
extra
question
sol-
was not really.
No, that's a good question. What happens to the extra solar energy if the batteries don't need it and the load doesn't need it? That's a good question.
In reality, like, sorry, not reality, the practical thing would have what we call a dummy load.
Okay, yeah.
Yeah, so you'd have a load, like you dump any excess energy on it. It doesn't happen for you here, like,
No,
I'm
but
I'm not
that's a good
thinking that
question,
you.
though. That's a
yeah.
good question. Is there a dump load required for this system?
As far as I know, I am honestly not certain. I would say the charge controller probably has some sort of internal resistance that it can dump that excess current through. But I would definitely take some more research on my part.
Or what would
Is
be
that-
the easiest way of doing
Yeah,
it?
is that what happens though, or
Yeah,
is,
no, what's the easiest way of doing it?
It would just be to add an extra load to the system
No.
that's.
Come to ground.
No?
No, it opens the line. It's not like a turbine or if you open the line, how much power does your solar panel deliver?
right,
0.
yeah.
Disconnect, so he, instead of having a dummy load, just disconnects,
Yeah.
yeah.
Now, if it was a windmill or something like that, that's a whole other story, because then you get into the inductive properties of the generator, and then you do need a.
And the wind turbine running out of control.
Well, yeah.
Exactly.
I have another one.
Yeah.
No, that's a great question of which you
Yeah.
need to be.
I'm sorry, but
defend
I,
yourself on that.
Yeah.
I'll try to be nice, okay?
No, I thought that was a good question that you had.
I mean, when it comes to sizing of your battery, like, did you pick that, or was it like proposed to you, or?
For the sizing of the batteries,
Yeah.
it was, the batteries that I chose were basically, they were provided by NBCC, so,
Oh, you took one over there.
yeah, they were provided, so it was just something that,
They were long.
Yeah.
yes.
And do you know how charge controller works?
Honestly, I don't know the exact internal specifications
Okay,
of the
if you
charge
could name
controller.
just the main component, what is it inside? Okay, what's that MBPT?
Maximum power point tracking.
Tracker. What is that? You took a BB course, right?
I did. It was a long time ago now.
Oh, it's okay. I was just wondering. Okay.
Yeah, I'm not sure.
Okay, think of this. Okay, is always your PV panel gonna provide you the 12 volts? Are you gonna get the 12 volts every time from a PV panel? From the PV panel?
Yes, the panel should provide at least 12 volts or more.
Every time.
All the time, yes.
You're sure?
From my measurements, the PV panels, even under low insulation, were roughly like 20 volts open
What if it's
circuit.
hot?
I put a short circuit across the PV panel. It's gonna provide me 12 volts.
Oh, if it's short circuited, it won't provide any
Okay, so
voltage.
it's
The voltage,
99% of the short circuit. It's like any other source, it's gonna,
change.
Yeah.
So inside the charge controller, there's a converter there that regulates. You already said that regulates. You mentioned that regulates the voltage. So basically, it's changing.
and what's it trying to achieve no matter what the voltage is?
Well,
It's trying to achieve the maximum power that can be received from that amount of voltage and that amount of current that it's receiving.
Well, it's trying to change one, which is going to be the current, for the amount of voltage being produced. Let's not forget that PVs are voltage sources, right? So if it only can put out 6 volts, there's only a certain amount of current that relates to that it can produce. So it's going to try to look like that type of load to the PV panel to be at maximum power.
Yep.
Right? Maximum power though doesn't mean it's going to be maximum power of your panel or of your charger or whatever. It's going to be maximum power at the conditions there are
Yes.
at that time.
Yes, that makes sense.
Yeah, time's up, but can we just ask one more question here?
Go ahead.
Oh, thank you. This is an easy one. Well, it might not be actually, but it's not intended to be, to stress you out. First of all, I just want to say that I liked how you worded, you know, you called this yours, and you know what I mean, in the video, and I thought that was important because this is a community endeavor, and everybody has a part in it. You had a part in it, the CRHS students had a part in it. There's a lot of people that are involved, and I think that was important that you said that. But for the benefit of those here, could you quantify the hours that you put into this project? Not just, don't include Mr. Furt and my hours as a stakeholder or anything like that, but just your own hours that you put into this. If you were to include the nominal course hours, but I know you spent a lot of time outside of that too. Do you have any idea how many hours you would have spent on this project altogether?
I would say roughly over the course of the past 6 months, I've spent between 350 to 400 hours on this project.
Okay.
Yeah.
You guys hear that? First year guys? That's what it takes to be successful in this, right? I just thought it was, thank you for citing that number.
Appreciate it, thanks.
Well done.
How difficult did you find interacting with the stakeholders on this project?
I thought it was easy. They had no issues.
Okay, we're gonna. I didn't know I could do that. I thought only you could do that. Okay, we gotta get started here because we got a meeting to attend after this, so we gotta be on track. So I'll try not to trip here. I know this is all has a purpose, so I don't want to ruin your demonstration. Coming up here over the next hour here, we have Mr. Trent Cormier, and he's going to go over his analysis of PV Coordinated Systems project. Take it away, Trent.
Thank you, Mr.
Okay.
I'm Trent Cormier, and I'm going to present analysis of PV Coordinated Systems. I'm an alternate energy student, and my advisor is Mr. Lish over there. An overview of what's going to be covered today. I'm going to go over the purpose of the project, reasons of why I did do projects, the benefits of the project, and what it could present later on in the future, the block diagrams, concept drawings, parts list, wiring diagram, schematic, testing, block diagram, how the project is completed, function, testing results, and conclusion for this presentation. So the purpose behind this project here is to find out an answer to a question that's being asked. And that question that's being asked here is, can a solar tracking PV system generate more energy than a fixed solar system? And if so, by what degree? Another reason of why I decided to do this as a project for this year is climate change. We can already see the effects of climate change all over the country, in the third world, as well as here in North America. So you can see it down here on the bottom right here. These are the global temperatures that are reaching up to 1.2 degrees C, and it's the data that has been taken from the National Environment Association there, which is in the reference at the bottom of the references there, back of the presentation. Benefits to this project. The solar panels do not emit any greenhouse gas. However, in the manufacturing process, there is a possibility of using greenhouse gases, emitting them into the atmosphere when making these modules. But it's not to defeat the purpose of when you're trying to harness energy that you aren't emitting any greenhouse gases in the air, causing global temperatures to rise. Possibilities for clienteles. There's a lot of applications that solar panels can be used for, many applications. One being to power your home, or even to power a facility that is looking to manufacture anything. There's many applications that these modules can be used for in order to, make it in a cleaner environment and kind of delay the inevitable of climate change and stronger effects over the course of the year or century. Along with saving money as well, you can save a lot of money on your power bills depending on the size of your system. This is just a small demonstration, so it's nothing major, but obviously if you do have many more panels, you can save a lot of money on your power bill at the end of the month there. So I'll go over the block diagram here. This is the block diagram of the project. So you can see in the top left corner here, sunlight, and we have PV module fix and PV module track. So photons, which are being emitted into the atmosphere by the sun, will strike the modules, generating the photoelectric effect, and that photoelectric effect will have electrons going through, which is current, going to the charge controllers, which will then regulate the charge of the batteries, the lead-acid batteries. You can see here, down at the bottom here is the DAC. That is what is used to collect any data on voltage and current parameters and understand which system is more efficient and what is the purpose of these two systems and how we can conclude to this. So you look in the right corner here as well. PV module track, you can see that there's a motor and the motor control. So those two components right there, those control the orientation of the photovoltaic and the direction from east to west, tracking the azimuth. This is an important aspect because obviously with more direct sunlight exposure to the modules, you're going to see an increase in current, meaning that the charge rate can be higher, and I will go more in detail over that over my data gathering there. You can see there's a DMM back there. That is essentially to measure voltage and as well as along with current if the need is for it, to see what the draw is of the motor and what the losses will be from the battery. And and then we'll go down to the analysis and understanding these parameters and how efficient are these modules. You can see down here the PC and the question. So the PC essentially is wired to, well, using it via USB, you can see that we're going to have data that's going to be stored into the PC, and then it will be exported into Excel, into graphs, along with tables as well. And the question back there in the bottom there, that is to go along with the question in reference to the analysis project. So this is the concept drawing of the track system here. We got a front view, top view, and along with the side view down here. Top here, you can see it is the wooden structure that we are using to displace the LDRs from one side to the other side. As the sun does track from east to west, it will cast a shadow on one of the LDRs, causing it to shift in the direction needed, clockwise or counterclockwise. Down here, you can see that the motor is mounted. We are using a rubber fitting along with L brackets that are mounted to the top of the piece of stand there, the plywood. This enables it to be secure, so that way there's not going to be any torque problems or friction problems there. And we do have a swivel that is between the plywood, just because the reasons that we don't want to have a lot of torque problems, and we want to make sure it is a free-moving module, tracking easily without any problems. You can see here at the top as well, you can see the PC along with the LCD and the shunt. The shunt essentially it was used to discharge the battery, so it's not in relevance to this project as much, but it is a need to know at what state of charge is the battery, and what are the parameters we're going to see over the course of time here. In the side view, you can just see the same illustration. Notice the mounting brackets as well. They are angled to about a 90-degree angle, just to make it an easier view in the eyes there. However, I will go more in detail about the degree at which it will be angled at. Going over the concept fixed here, this is more of a simple build compared to the tracking system, as there's not as much requirements for a motor and mounting a motor. You can see we do have stands at the bottom here, or legs if you want to call them. They're basically there just to prevent warping of the board. However, it does happen on uneven level of plane. You're going to find that it will cause warping of the board. So a more secure structure would be definitely needed later on in new revisions. But we can look over here as well. You can see the mounting brackets as well. These stands, which are also used with drill bits. So we use wooden screws for that to hold those in place. And you can as well see the mounting brackets at the 90-degree angle there, and all the dimensions that are given in inches. The concept enclosure. This is definitely one of the most important aspects to the project, because this is where all the data gathering is going to be happening and the observations that can be made throughout the project. You can see that the DAC is mounted to a piece of plywood with N3 20mm screws, just basically holding it up in place so that way it's not going to be sitting down where the shunt is or the battery, having any short circuit problems. We don't want to come across any of those. So you can see down the bottom left and bottom right corner of the front view, we get the batteries. Those will be used for the charging state of the systems to see which system is more efficient than the other. And we can see the charge controller as well. They are placed right in front of the battery. It looks a little awkward at first, a little bit to see that, but I'll show you a little demonstration here later on to see where they're all positioned here. And we do have the shunts just on the side of the charge controller. Essentially, I'll go over the wiring diagram afterwards to cover on topic of the relevance of how we're going to measure the current going into the battery. You can see that this enclosure also helps, if it's raining, we can prevent any water damage to the system or devices that are placed in it, as we do not want any water going in there and causing any troubles. So whenever it's raining, obviously toss the top lid on and you can prevent those measures and have the wires come out the sides of the enclosure, as I'll show later on there. This is the parts list that I've compiled together with everything that I've used throughout this project for both systems. As you can see, it's, it's not fairly a cheap project if you're wanting to buy every component. However, thankfully NBCC was able to supply the DAC, which is an expensive device. You can see that is around $300 there. So thankfully NBCC and the instructors allowed me to use that device, so it can save me some money there. So the total of this project was around $1,850 there. It's pretty pricey. The modules were $109, so starting the baseline there, the modules are $109 tax. You're looking at quite an expensive project, including with the batteries as well, along with being $40 a piece there. So you're looking at $81 for the batteries, and as well as the components that are put in together to make up the controller. This is the wiring diagram for the project. So you can see the two systems are side by side there. You have the track PV module and the fixed PV module. Starting up from the top left corner here where the PC is, you can see that there is the USB port going into the DAC via the PC. And we have 4 analog channels that we're using. So these 4 analog channels are going to measure the voltage and the current parameters. So you can see the 100 millivolt, 100 amp shunt, which we have wires 22 gauge going to the sides of the shunt. And then we have our 12 gauge wires on the top of the shunt going to the batteries, which is 12 volts there. And then we can see that we have on channel 2 there, that essentially is, that is used to measure the voltage across the battery and understanding what the voltage is in the charging moment there. Shunt's used for current. You can see on the other side of the shunt 2 there, it's the same idea. We do have the shunt used for current and the 22 gauge wires going across the battery to measure the voltage across the battery there. The charge controllers regulate the voltage to the battery. You obviously do not want to throw a photovoltaic rate on the battery because you're going to run into issues of overcharging and possible damage to the battery. We do have 14 American wire gauge and 10 American wire gauge, rated to 12 American wire gauge. So the thing I noticed with the energy systems that I used in this project is that the sizing of the MC4 wires were 14 American wire gauge. I couldn't find anything similar to that, so I decided to go to a 10 American wire gauge extension, and then using the charge controller inputs as a 12 American wire gauge with a 10 amp fuse there, sized to the charge controller. Looking at the motor controller schematic here, we can see that there's an LM393, which is the main component, I would say, to this project. It is known as a voltage comparator. So what it does is you have 2 photocells that go into the inputs of the LM393, and they monitor the voltage of those 2 LDRs there. So there's also the variable resistor, which we have, that is going to be used for the inverting input, and we have the other 2 inputs, which are the LDRs, as the non-inverting input. So the state at which it will rotate or change direction is whenever the voltage is greater than the variable resistor voltage. So as long as it is greater, it will rotate clockwise or counterclockwise, going to the L293D, which is the motor driver. This basically allows for bidirectional control of the motor in clockwise or counterclockwise direction, allowing for the free movement. And we have a 5-volt regulator at the top there. That's used for one of the pins on the L293D, as it's important that we make sure that the voltage is the correct voltage on the input for that. And we have the motor going on the outputs of 1Y, along with the 2Y there as well. It should be noted as well that this can control another motor as well, but this is a single axis system. It's not a dual axis system. Dual axis systems, it's another topic there we can go on later on in conclusion. So the testing that was to be completed for this project was to use a light meter or a pyranometer. which measures the amount of light that's going to be striking the modules. And it's important to note what the daily solar installation could possibly be. Of course, it does change over the course of a day though. So you can see that the data will be logged, of course, into tables or either taken down in notes. And PV modules will be then compared with the output of which the DAC is going to give, and we'll make the results and find out what the conclusion would be to that there. And this is the other testing that we'd be doing today, or not today, but doing, that we did do. It's using RedScreen Expert. This is a software that utilizes anything from energy you're looking to find. So there's the angle of incidence that we're going to be finding out of the optimum tilt angle, of which angle is the most significant angle to be using for the design month of May. This would be different if you're doing a yearly basis system or if you want to do a 6-month system. But if you do want to change the tilt angle every month, that is an option that you could do to get as much energy as you want. So we'll observe the data collected and we'll come up with an answer for that as well. So these are the two systems that I had set up. This is my grandparents' backyard. They had a lot of space, so there was not a lot of shading analysis when it came down to the project. It was a great setup for it. And we did have, of course, the counterweight just to balance out the system and make it so that way there's not as much torque on the motor itself that I did an angle there. You can see the enclosure down there as well as the laptop. I wouldn't recommend leaving it in the sun as there can be problems, overheating of course, so I did recognize that after the fact and did make changes to that. The energy system that I'm using is a 100-watt monocrystalline. You can see the electrical data on this. It's 100 watts, open circuit voltage of 24.3, short circuit current of 5.21, optimum operating voltage of 20.4, optimum operating current of 4.91, module's efficiency is 17.8, and the maximum system voltage is 600 volts DC. Maximum series fusing rating would be 15 amps. We're not doing a 600 volt system, it's just to observe the two different modules in comparison, so we don't need to worry about that there. As you can see here, this is the enclosure that I have. I've labeled everything in coordination to for which system is going to be used. Battery 1 and battery 2 can be interchanged to kind of get the best and most accurate data. Just to understand, because if one battery's been drained more than the other, you of course want to swap them out and see the difference between the two there. Shunt 1 and shunt 2, like I said earlier, those are used to measure current. So we do have red wire going to one side there, and then we have the black wire which would go to the positive terminal, not the negative. And we have the DAC, which of course has the 22 American wire gauge going to the positive and negative terminal to measure the voltage across the battery there. It's the same idea for the fixed system on that side. And we do have a thermometer. The only thing is, when the thermometer is sitting out in the sun, it can be inaccurate, as I found out one day it was up to 40 degrees and it was about 28 degrees. So sun exposure can have an effect on that thermometer there. So this is an example of the charge time for a battery, depending on the amount of current that's delivered. But current does change in respect to how much sunlight exposure there is. So if you find that this tracker is facing south and the sun's more out west, you're not going to have as much current delivery because it's not perpendicular to the sun. Whereas the tracking system will be following it, having more current delivery and a higher rate there. So I did a battery, 7.5 amp hour battery, 12 volts. So divided by the amps that are supplied, you're going to find around about 3.75 hours, which is about 3 hours and 45 minutes there. This is the controller. It's in a breadboard, and I put it in my mom's actual cheese box. That's what we called it. We've actually put cheese in there in the fridge, but she allowed me to use that there for the project to kind of keep it in a small enclosure. You can see here, this is the LM393, and then we have the L293D, 5-volt regulator, variable resistor, and their LDRs, which would be equipped to the brown and purple wire, which is external to the breadboard. So I'm going to go over the data that's going to be acquired using the DAC 245 for the voltage and current. these are the tables for the systems that have been measured. So we have on the left side the current, which is amps, fixed build, and the track build. Same idea for the voltage, and as well as the power delivery there. So we can find that over the course of time, there was more current delivered to the tracking system as there was more sunlight exposure. It was facing the sun most majority of the time and track it. However, it does become mechanical problems over time, but they can be fixed just by troubleshooting. So you can see here the range of time that it was at 4.13 amps, and we scale down to the middle here, looking at 1.23, 1.24. So it started to even out over the time there, and by the end of it, we had about 0.37 to 0.28. And that's because there was a faster rate of charge, and they're both sides the same size for the batteries there. Take a look at the voltage here. We can see the fixed voltage for the fixed system there and the tracked voltage. So we can see it did start at 13.39 volts for the track build, and we had 13.56 volts for the fixed build. But if you look at the bottom here for the 30 there, it does actually say 13.80. So even though there was a difference in the voltage between the batteries, we did find that there was more current delivered, increasing the voltage of the battery there as the capacity it's stored, and 13.71 for the fixed build. If we take a look at the power delivery, we can see that there was more power delivery over the course early on than there was later on, due to the fact that there's only a certain amount of capacity that can be stored in the battery per se there. So this is the graph for both systems of the current. You can see it started around 5 amps, started to make its way down there. This is a scaled version of time intervals of 5 minutes, since there were so much data points. So I decided to collect data and average it over 5 minutes to understand which system was more efficient. So we see the fixed system there. It does start around 4.2 amps, I would say, and courses out down, and it does level out more compared to the track system. The track system, like I said, there was only so much capacity that you could store into the battery there. So it came down to how fast the charging would happen on the system. And this is the voltage. So you can see that around 13.4 for the track system and around 13.55 for the fixed build. It does scale up higher as there was more storage onto the track battery in comparison to the fixed. And this is as well as the power delivery there. So testing that was done for the project, I used a light meter and scaled it at the 100 rate there to see what we were going to get for the amount of not daily solar installation, but the amount of light that's in the moment at that time. This was taken at 1:41 p.m. May 12, 2022, which is corresponding to the data that I have collected and stored on this presentation here. So I used a constant of 0.078, which I found as a source on the research aid, and they said it was common to use for higher scale light meters, which this is here. So I took 1089 times 100 and times that value to get 849.92 watts per meter squared. This worked out to be around 85% of what we're going to say to the STC conditions of the module, because the conditions at which these are labeled, they're labeled at 1,000 watts per meter squared at 1.5 air mass and at 25 degrees C. So it's going to be different reading from what you're going to find in comparison to in the moment. So if we go back here to the tables, referencing the number 5 increment, which would be about 25 minutes into the project there, we're seeing that a current delivery of 4.10 amps, which I believe to be an accurate reading in comparison to what the readings are for the maximum if we go back further here. So you can see that the short circuit current is 5.21 and the optimum operating current is 4.91 amps. And testing for the optimum tilt angle. So it was found that 15 degrees was the best optimal tilt angle for the month of May, as there would be a daily solar radiation within tilted systems in the middle section there in kilowatt hours per meter squared a day. You're going to find 5.24 kilowatt hours per meter squared a day. There are limitations to this, as the battery size was sized up to the motor and not sized up to collect data through an 8-hour session. So I didn't find this was the best testing to be doing for the system, which should have been revised afterwards there. So the data required, I'm going to show what it looks like here, and I can conclude that yes, the tracking system was more efficient there. So you see 12.097, this is for the first system here, 12.054. No current was delivered at the start, of course, but in respect to time, afterwards we did find 14.09 and 14.230 there. And that was for the tracking system, and this was for the fixed system there. In conclusion, yes, the tracking system, I believe, is more efficient, as if it's following the sun, you're going to get more sunlight exposure to it, so you're going to have more current delivered to your battery there. Obviously, it would have been better to have a larger battery for the system, and I believe, because 7.5 amp hour 12 volt battery, you can't get a lot of data over courses of days, or I should say the day, just because it's not designed to be charging at a high rate all day, and you'll see current will go down as the capacity is stored. So what's next? I think what I should do is, I'm going into a new home there, I'm moving out into a new house, so I might use these systems to power my shed, depending on what loads I might need to power it to, drills or even lights in that there. These are the references that I have, and I'll do a demonstration here. I'm not too sure why it's not loading up on the presentation here, but I can go around and kind of give you a demonstration of what it looks like here. As said earlier, it was using the DAC hardware software there, so I will actually show this one more time just to see. So, going around here, it's very hard to see, I would say. But you can kind of see on the top here, we do have a reading of 12.51 volts there, and 0 current delivery because the system's not getting any light right now, so you can't really demonstrate that there. But using this software here, I did utilize it and find out the current and the voltage parameters of which the system was being charged at there. And unfortunately for the tracking system here, I can demonstrate what's going on right now, but I believe there's to be a short going on, so I will get one of the batteries. There will definitely need to be some troubleshooting for this here. So you can hear the motor working, and it's believed that it might not be coupled or that there's a possible short because there shouldn't be any motor movement at all as the LDRs are at equilibrium for the amount of light that are striking them there. Questions?
Mr. Juha?
Oh, you can start.
No, go ahead.
Then you go back to your block diagram where you have the sunlight there.
Yep.
So what is it that it's going from the battery to the motor control, that line?
So this is actually fed through, so the motor controller and motor are actually powered via the battery. So when the system's working, it's not so you have to have another battery to power up the motor and motor controller, but rather just use the battery that's being charged up with the tracking system instead.
Yeah, so you're using the same battery that feeds to the DAC to the control the motor?
Exactly, yes.
Like to power the motor itself?
To power the motor, yep, because there's a motor controller which has the components to control the motor. An op amp does not draw a lot.
And the control of the motor is based on the voltage?
Yes, depending on the LDRs. So wherever has a greater voltage on the left side or right side, it will change the direction to go in that way, getting the most amount of light exposure.
And that doesn't affect your system at all?
No, I didn't find it affects my system, but there was a current, the motor itself powered, it took about 8.16 watts. So it's 0.68 draw, and it's 12 volts. So I did find there was a little bit of losses, but it was nothing major where it would be saying that the tracking system is less efficient than the fixed system.
Okay, I do have some. Can I continue on?
Yes, please.
Go into your testing. Where you test your light?
Testing the...
I think where you test the light. When
Oh,
you have
the power? Yep.
Yeah, meter, yeah.
Did you want the block diagram or did you
No,
want
I want to see the values, the results. Oh, yeah, here. Okay, so you're getting, what I see there, that you're getting 849
0.42.
watts per meter.
Yep, but that's based on the STC conditions. It's not based on 1200 watts per meter squared. It's just based on the STC conditions, the percentage of what it
Wait for the
is.
question.
Okay. Do you know what's the STC condition?
Standard test conditions.
No, what are they?
Oh, the standard test conditions? Sorry, it's right here. So this is the standard test conditions for the...
No.
No, what my definition is the
What's the temperature?
Those are how your PVs react at STC. What
Actually, this
is
is, yeah, actually, this is more helpful.
Yeah.
Sorry.
But I wanna know what STC is.
Yeah,
So are you talking about like the 1,000 watts per meter squared, temperature?
Yes.
25 degrees C, air mass 1.5?
Yes.
Sorry.
That's
yes,
your
yes,
STC.
sorry.
okay, so if you're getting 849 watts per square meter, right?
Mhm.
From a 100 watts panel. What's the maximum you got? Because in the results I saw that you got 66.
So 66.
Like in one of the tables there where you have the results. Yeah. So the maximum you got for power there, or 69. Oh, you got 69. Oh, far.
Oh, power,
Yeah.
the power,
Yeah.
sorry. So it's not exactly gonna be, it's a constant that's used, so it's
Yeah.
not the exact value, but it's a
Oh,
constant that,
No, what I mean is, yeah, that validates your test, I'm thinking, because you're getting, yeah,
It's something-
69.
So my question is, yeah, it's 69 versus what they say it was.
849, which is
849 watts.
out of 100, so 70 out of 100 is not,
Yeah,
It's not
so-
yeah.
But my question is though, can you go back to the picture of the meter there for a second?
Oh,
Yeah, the light meter.
sorry.
So you have this light meter here that reads in foot
Lux or
candles.
foot candles.
Yeah, lux, you have a luke there.
yeah.
I didn't know what luke was.
Sorry,
Okay.
yeah, that's supposed to be Lux, L-U-X,
Okay,
sorry.
makes more sense. And foot candles, and then you had to do a conversion, right?
I had to find a conversion. There was very minimal sources to find a conversion ratio for Lux or foot
How
candles.
come you
It's
didn't
not-
use that pyranometer that we have here that would give you exactly the insulation?
I didn't know the pyranometer, I only knew with the light meter, as I
We
found,
have-
you have a pyranometer, right?
Yeah, pyranometers here, we have two of them. Three?
Two. Unless you got one.
Nope,
Okay,
we have two and a broken one.
two.
Don't use that one.
No, yeah, don't use that one.
That would have made it a lot easier,
Sure,
a lot easier,
and probably much more
Accurate.
accurate.
very more, yeah.
Okay, all right, so anyways, I was wondering why
Yes,
you
that's,
did this, so that, you know, obviously you were unaware of the devices that they
That's kind of my fault.
no.
One last one,
I
maybe?
found that in the e-building, so I gave him that.
Okay. But nonetheless, you were able to do a conversion and you
Yeah, it wasn't,
estimated
it's the cost that I
800.
found, it's not like the most, it's what I found the only sources.
So you've got 850 watts per meter squared,
Yep,
and then I'm assuming in your test results,
Not all of them.
those were, that you were showing a while ago was what you were actually reading.
what I actually was reading, yes,
And
and
then-
it wasn't exactly what I was looking for,
Okay.
but it was around a certain value.
Well, there's gonna be bound to be errors.
It-
right?
yeah.
Yeah, sorry, I just,
No, go ahead, please.
no, I was done, I want to question
Okay,
one.
I have a question,
Yeah.
like, since you're doing analysis, right?
Yeah.
You're answering a question.
Yes,
Your question was, which one is more efficient?
so to a certain degree though, right? So, I mean, there's a lot of mechanical issues that come with the tracking system.
No,
and-
sorry.
Oh,
I
sorry,
want-
you go ahead, yeah.
Like, you, correct me, you're looking for efficiency, right?
Which one's more efficient? Yes.
Okay. Efficiency in terms of cost or,
Efficiency in terms of output power, so more so power or voltage that's being,
okay, so just electrical wise.
exact electrical data.
So you're not looking into the cost?
No, cost is, I did look into the cost, I found that this system did come up to around $400, and this one was around 200, including the wood, 250. Wood wasn't exactly the most cheapest thing to buy, obviously, but the thing with these systems here is that if I was to have two systems for the fixed system, you'd be looking at around $218 there, where one system here, you can maybe get more energy out of one system than having to buy two systems and more cost or whatnot.
Okay, my question, the other one is, you must did some research. Does the controlled system, have you ever seen a large scale of a controlled system being
Few.
installed?
And they're not the easiest to install. They actually are quite expensive. I found they use they put poles into the ground basically, and they use a, I think it's like an attenuator, I think, or
Yeah.
it's one of those motors that pushes out a
Linear
post.
actuator.
Yeah.
Actuator, thank you. It's an actuator they use. I didn't think of that idea just because I was thinking about the cost of putting something in the ground, digging and everything like that. So I wanted to use a stand instead and use a piece of plywood. Is it as efficient as using the other way? Probably not. It'd be more easier to
What
use.
a good next year project.
Yes, absolutely. That would be a phenomenal project to do,
Should have
actually.
been- Should have been your conclusion.
Yeah.
Like the efficiency, how percentage-wise, which one is more?
Percentage-wise,
Do you have that?
more so, I only have the data collected in comparison to voltage, current, and power.
But you were conclusive. You said like this one is more efficient.
More efficient in a sense of the current delivery and as well as the storage of the voltage in the system.
But I think we need to talk about power.
The
though.
power though,
I think current and voltage are
two
irrelevant.
different, yeah,
In fact, you should really be talking about energy, but power is a good, you know.
it's a roundabout kind of.
Well, yeah, you would say. So based on your findings for power there,
Yeah,
you're saying that that one's better than that one, but you should have had a,
there was
overall-
little limitations I found just because with the storage of the battery, it was a small battery. I really should get a large scale battery. 7.5 amp hour battery. I couldn't find as though the data would be more accurate, more accurate, not shouldn't say one more accurate than the other, but it was a smaller battery, which means it wasn't at a large scale, which I should have done a larger scale battery.
you could have just put power supply. Yeah.
Power supply.
Yeah, because I mean, I can see some very similar numbers there, but then.
It starts to even out at so in the end there, yeah.
So then that's the question, so again, I think you should have either time of day
Yeah.
or, you know, I mean, it's very, at the start, you can see that there's a significant difference.
Yep.
But then afterwards, it starts getting similar, but your numbers start decreasing too.
Exactly.
So is that because of the time of day, is it because of?
This was taken around 5 or 6 o'clock, so the sun was more in the west, but this was facing the sun. So I believe it's to be the amount of current that could have been stored in the battery itself, just because it was sitting around 14.2 on the charge controller, but as you can see on the respective of the DAC, it was saying 13.80.
But how long of a time frame should it have been to give you?
3 or 4 hours, which
Just 3 or 4 hours?
because I was calculating the charge time for theoretically on the battery, and I don't think it would have been fully charged before 8 hours, I believe.
I don't understand why you keep referring to the battery personally. I think what you're supposed to be looking at is the amount of energy collected.
Energy collected, okay.
And the idea with that rotating and that not rotating is that one faces south all the time, and that one doesn't, right?
Exactly, yep.
So that guy maximizes his efficiencies
Yep.
at noon hour,
Yep.
near noon hour, and that one tries to spread it out more,
Exactly.
okay? So it doesn't matter what your battery charge is or whatever, as long as,
It's more so the power that's going,
well, as long as your system is working.
Yep.
And you've got a load on it, then you can read the load, right? You know?
Absolutely. Does it, would it automatically search for the sun in the north?
it does, so so the only thing is I never actually kept the system outside, outside all night, so where in the morning sun would be coming up. I didn't feel safe leaving the system outside, just in case, so I put it in the garage. I more so set the system up around 9, 10 a.m. And it would track, as soon as I set it down, go in the direction where it needs to go, where it was east, and then track obviously in increments going west. And it wasn't full power delivery. The motor isn't getting power delivered all the time, because it's only when you notice the difference between the voltage of one LDR or the other is when it will turn the motor and then go, drawing power there.
Did it hunt when it was facing the sun? Did it hunt?
Hunt?
Go back and forth, back and forth, back and forth?
I didn't find it hunted, but more so, I found that when I didn't have counterweight, it more so kind of got stuck at one point, and I believe there was probably a bolt that was catching on the plywood, which was addressed afterwards and fixed. Yeah.
Just a quick question. I
Yeah,
don't know,
yeah.
because I may be wrong, but does the track power have to be like always higher than the fixed one, or does it make sense that it starts higher than the fixed one, then at a later time, like the last 10
So that's what I was in
rows,
reference to, like the
it's
charge.
lower?
Yeah, it
for-
starts to
for
go
the
lower,
track
like the
than-
3,
than for the
exactly.
fixed.
And I believe that's because of when it reaches a absorption or float charge, where it's getting current delivered to it, but it's not a high amount of current as the battery is getting charged up to its almost its
So
maximum.
when the battery is charged, the flow reduces. So that's the thing about the battery side.
That's what I found
It's a
that was the
coordinated
problem,
system.
and that's why I should have
It's
had
not a
a larger
photovoltaic
battery.
study, it's
Yeah.
a system. So that's how the battery factors in.
Oh, okay, that explains.
That's it.
Yep, good.
And Mr. Parker, you are right, changes in perspective.